Computing Machines and Automation. A.V. Aston. Tape Identification and Rerun. Procedures for Tape. Data Processing Systems. L. Ilson. Conference on Electronic Digital Computers and Information Processing, Darmstadt, Germany. October 25 to 27, 1955, Titles and Abstracts. Of papers. CTC components shown include A capacitor, B standard and in. Solated terminals, C coil for IIL, kit, D RF choke kit, E coil forms. And coils, F coil kit, G RF chokes, H diode clips, I panel hardware. J standard and custom terminal boards, K shielded coil form. I. One big family with a single thought. Whether you need terminals, clips, coils, chokes, capacitors, or any of a number of electronic components, you can be sure they're right if they're made by CTC. One continuing basic idea governs the manufacture of every CTC product. And that idea is quality control. We could not guarantee our products, as we do without a constant check of numerous details that determine really able performance. Our quality control engineers see to it that these manufacturing standards are consistently maintained, right through to periodic microscopic inspection. Pictured here are a number of components available at CTC, including our 3 kits. These items come in standard forms and are also custom engineered to meet your particular requirements. We would be glad to give you complete details, including specifications and prices, on any or all CTC units, as well as information on how CTC components can be specially designed to solve your individual electronic components problems. You will find it well worthwhile to use components that are guaranteed right to CA Bridge Thermionic Corporation, 430 Concord Avenue, Cam. Bridge 38, Mass. West Coast Manufacturers Contact, E.V. Roberts, 5068. West Washington Boulevard, Los Angeles. 16 and 988 Market Street, San Francisco, California. Cambridge Thermionic Corporation. Makers 0/guaranteed electronic com J. Jonant Slow. Custom or standard. See the CTC components on display at booth 502, IR Show, Kingsbridge Armory, New York, March 19 to 22. Computers and Cybernetics Robots. Volume 5, Number 4. Automation. Automatic Control. April. Established September, 1951. Articles and Papers. Computing Machines and Automation. Tape Identification and Rerun Procedures. For Tape Data Processing Systems. Reference Information. Forum. Conference on Electronic Digital Computers and Information Processing, Darmstadt, Germany, October 25 to 27, 1955. Titles and abstracts of papers. Computer People, Master File on Punch Cards. The Computer Field, Products and Services. For Sale Headings. Entries. Publications for Business on Automatic Computers, Reference Listing Part 2. Net Patents. Association for Computing Machinery Meeting. August, 1956, Los Angeles. Wayne University, Detroit, Summer Program. On Computers, July 23 to August 11, 1456. Removable and interchangeable typewriter type. Footnote no, trailer note. The editor's notes. Index of notices. Advertising index. A.V. Aston. L. Eelson. E.C. Berkeley. N. Chapin. R.R. Skolnick. A.W. Jacobson. A.C. Hancock. B. Danch. 1956. 6. 12. 14. 20. 23. 24. 28. 40. 30. 37. 4. 4. 48. 1 editor, Edmund C. Berkeley. Assistant editors. Neil D. MacDonald, F. L. Walker. Advisory Committee, Samuel B. Williams. Herbert F. Mitchell, Jr., Justin. Oppenheim. Contributing editors, Andrew D. Booth, John M. Breen, John W. Carr, 3, Alston S. Householder. Publisher, Berkeley Enterprises Incorporated. Publication Office, 513 Avenue of the Americas, New York 21, NY. Algonquin 5 to 7177. Editorial Office, 36 West 11th Street, New York, 11, NY. Graham Y 7 to 1157. Branch Office, R15 Washington Street, Newtonville, 60. Mass. Decatur 2 to 5453 or 2 to 3928. Advertising Representatives, San Francisco, W. A. Babcock. 605 Market Street, San Francisco 5, California. Yukon 2 to 3954. S. Angeles Wentworth F. Green, 439 So. Western Ave, Los Angeles 5, California. Dunkirk 7 to 8135. Elsewhere, The Pilcher. Computers and Automation is published monthly. Copyright, 1955 by Berkeley Enterprises Incorporated. Subscription rates. $5.50 for P.N a year, S 10.50 for 2 years, in the United States, $6 for 1 year, $11.50 for 2 years, in Canada, S 6.50 for 1 year, S 12.50 for 2 years elsewhere. Bulk subscription rates, SL, E page 43. Advertising rates, see _page 46. Entered as second-class matter at the Post Office, New York, NY. 3. The Editor's Notes. The IR Show for Computer People. We went to the INST of Radio Engineers show in the Kingsbridge Armory, Bronx, NY. Literature for the press provided SOMS Day. Statistics, there were nearly T110 miles 0 FEX. Hibits displayed in some 715 booths. The attendance was expected to be 0 VER 45,000 persons. The exhibitors at the Conventi 0N. Between them produce about 80% of the country's productive output in electronics. It was a tremendous show, really super colossal. The problem, however, that lies still have not solved is how an ordinary human being can the SHIV, with a reasonable degree of mental absorption of the new ideas presented. Total time the SHIV was open came to 43 hours. Over 4 days, or 2,580 minutes. If a man said to work to see every single exhibit, he'll would have only 3 minutes for each one of the 715 booths. We spent most of an afternoon there, and saw 4 or 5 exhibits, to the extent he Of really finding out something we want a D2. Not backslash from what they were exhibiting. We went to the show interested in compute. ERS, and O Tyler features closely 1 rupee 8 D2. Computers. We thought at first that the EX. Hibby tours that had something related to computers would be on Computer Avenue, but then we found out this was not so. But it was quite impossible to find all the computer exhibitors in the time LVE had. Now the IR directory is well organized, so that if you want to find out something about computer organizations, you can find them all listed in the same place, together it so me. See ordinance about them. ALS0, the IRSCHEDU1E. Of technical sessions is well organized ed, S0. That if you are interested in electronic computers, you can find just the sessions that you want to go to. So why not provide FOR? Next year's IRSHITVA map and guide taught he exhibitors and their locations and TIF hat THEY. Have that is NEDV, for each of the many professional interests or subfields, SUC has electronic computers, that the IRSERVES. In this way a person interested in computers or some other subfield, could quickly find out Ivy here are the best things to see in the time he has, with a minimum of uncessary. Tripping. Who's who in the computer field? For the computer directory. CU1 Rentley LVE are mailing out a who's who entry.form to all computer people that we knoty of. The form asks for your name, your AD address, your organization, its address, your title, your main computer interests, year of birth, college or last school, year entered, the computer field, occupation, anything, else. On the form there is a notice as follows. The Who's Who section of the computer directory, which last year filled about 95 pages of the 1955 issue, has not paid for itself. So this year we request a nominal charge of $2 FROOL. Each person whose entry is printed, in order to help defray the cost of the Who's Who. The main reason for this nominal charge is that we look on the Who's Who as a service to people in the computer field, especially all Y2 employers and management advisors looking for good men, but because of the cost of the Who's Who, I've have to make some kind of departure from the free printing policy which we followed in 1955. Please express your V at FESPEL 0TF. I think the Riksted nominal charge is reasonable, and enclose my Who's Who entry and $2. I do not agree with the requested charge, but I enclose my Who's Who entry and $3.40 for which I order an extra 1956 directory at 15% discount, not returnable. Close my Who's Who entry and $2 he 1p. Defray the cost of the Who's Who. Other. If there proves T0b insufficient support for the Who's Who and we do not publish it, TIV shall refund the $2.00 and $3.40 payments. In any case please send us your completed 1956 Who's Who entry form. T. Index of notices. For information on advertising index, advertising rates and specifications, back copies, bulk subscription rates, computer directory, manuscripts, reader's inquiry form, Special issues. See page 48, 46, 44, 42, 30. See February, p36. 48, 42. Address changes. If your address changes, please send us both your net 11 and your old address, torn off from the wrapper if possible, and allow 3 weeks for the change. 4. Ultra-thin tape for bobbin cores is rolled to high precision standards for thickness and finish on our own 20 high cm cold. Reducing mill, beta ray controlled. J. Junior IR, FU Bulletin TCL08. Tape.wound bobbin cores. For computer applications. Includes essential data on applications and properties, fabrication, and testing of Arnold bobbin cores, lists s.standard sizes, etc. Address department. CA64. These cores, fabricated by winding ultra-thin tape of high permeability. Magnetic materials on ceramic bobbin cores, possess ideal qualities for use in electronic computer assemblies as memory cells. Specifically, their desirable properties include quite rectangular hysteresis loops, relatively low coercive values and high saturation densities, plus temperature stability and the ability to shift in a few microseconds from negative remanence to positive saturation, and vice versa, under conditions of pulse excitation. Arnold bobbin cores are available in a wide range of sizes, tape thicknesses, widths, and number of wraps to suit the ultimate use of the core. Magnetic materials usually employed are Delta-Max, square perm alloy, and supermalloy, in standard thicknesses of 0.001, 0.0005, 0.00025, and 0.000125. Special advantages derive from Arnold's position as a fully integrated producer of wound cores, able to maintain precise control over every production operation, melting, rolling, winding, testing, etc. Let LIS supply your requirements for bobbin cores or any other magnetic materials. WAC 5687. 5. Computing machines and automation. Testimony of DRAV Aston, Director, National Bureau of Standards. Before the Subcommittee on Economic Stabilization, Joint Committee on the Economic Report, October 27, 1955. I am pleased to respond to the invitation of this subcommittee to participate in the current hearings on the subject of automation. The invitation requested specifically that I discuss the experience of the National Bureau of Standards with computing machines and that I give views on the future of office and factory automation. Let me outline first the functions and objectives of the National Bureau of Standards. In order to provide a background for our activities in this area, the National Bureau of Standards is a federal scientific and engineering institution, established to provide unique and essential services to science, industry and government. Our most basic function is to provide standards for physical measurement, together with means for their effective use. This responsibility requires unusual competence in the science of physical measurement in all major branches of science and engineering. Because of the general competence of our organization on problems of physical measurement, it has been customary for other government agencies to seek advice and assistance from the Bureau on scientific and technical matters. With the rapidly evolving importance of technology in our national economy, this service function of the Bureau to other government agencies has increased. At present, approximately 2/3 of the Bureau's total program is devoted to projects requested and paid for by other agencies of the federal government. The Bureau's work on automatic electronic computing machines began as a part of the organization's Technical Assistance Program. In 1946, requests for such assistance came from 3 different sources: the Bureau of the Census, the Office of the Air Controller, and the Office of the Chief of Ordnance. The Bureau of the Census was exploring the possibilities of applying recent advances in electronics to their large data processing problems. A preliminary survey showed that the prospects are very good. This was followed by a contract placed by NBSTDTH, the former Eckert Mauchly Corporation, to prepare detailed performance specifications for a machine suitable for the needs of the Bureau of the Census. The completion of this contract was followed, in turn, by a purchase order placed by NBS for 3 large LK 6 data processing machines, 1 for the Bureau of the Census, 1 for the Office of the Air Controller, and 1 for the Army Map Service. This order was filled by the delivery of the first 3 UNIVACs. The problem brought to the Bureau in 1946 by the Office of the Air Controller required the services of both electronics and mathematical experts from the Bureau's staff in connection with logistics planning problems of the Air Force. A preliminary analysis of these requirements pointed to the desirability of having available at an earlier date a somewhat more modest computing machine than the exted UNIVAC. This led to the design and development by the Bureau of its standards electronic automatic computer, commonly known as the SEAC. The SEAC was placed in productive operation almost a full year before the first UNIVAC was delivered, and it has now been operating on an around-the-clock basis for more than 5 years. Also in 1946, the Office of the Chief of Ordnance asked the Bureau to study critical components and subassemblies for a data processing machine which the Army was procuring for its ballistics research laboratory at Aberdeen, Maryland. This led to an active program at the Bureau on the development of materials and components for use in the computing machine field, and to the development of reliable evaluation techniques for such components. A little later, the Bureau designed and built for the Department of Defense a mobile and more advanced machine, the DSERC. The DSERC was turned over to the Department of Defense in the spring of 1954 and is now in operation at the White Sands, New Mexico proving grounds. The availability of the SEAC, coupled with the Bureau's considerable expertise in this rapidly growing field, has resulted in numerous requests for technical advice and assistance in connection with the design and possible utilization of modern high-speed electronic computing devices. Before discussing more specifically the nature and importance of some of these requests, I should like to outline some of my own views concerning the importance of these new technological developments to our national economy and to our general welfare. The relationship of these developments to our economy is, I believe, closely associated with the interest of this subcommittee in the field computers and of automation. Automation is a relatively new word. It has been defined in many ways by various people. It probably means the process of rendering automatic. From this point of view, why the newest thing about automation is the word itself. The development of devices to pages reform functions automatically is a very old activity. For example, the ancient Romans invented a hydraulic float valve to control automatically the level of water in storage tanks. I would prefer to consider the subject of mechanization, which is a broader area of technology, 1/1th. Automation as one of its important subdivisions. The general goal of mechanization is increased productivity, to use machines to aid man in producing more goods and services. Increased mechanization and increased productivity have expanded together. This has been especially noteworthy over the past 150 years and largely in the past 50 years. Mechanization has several important phases. The first and probably the most basic is the replacement of physical energy provided by humans or animals by energy provided by machines, powered from mechanical, electrical or chemical sources. A primitive example is the use of hydraulic energy to operate a flour mill. More recent examples are the use of gasoline to propel automobiles and tractors and electrical energy to turn the wheels of factories. The importance of this phase of mechanization is attested by the tremendous expansion of electrical and petroleum energy sources in recent decades. Even more phenomenal expansion can be expected as atomic energy sources become available. A second phase of mechanization is the use of physical measurement. In the older days of hand craftsmanship, items were fabricated by fitting mating parts together or by adjusting an item, such as a garment, to the individual size of the user. With the development of the science of measurement, together with instruments for making measurements, it became possible to fabricate items according to specification. When items are fabricated according to physical characteristics, as defined on a blueprint or specification, they can be used interchangeably. Developments along these lines led to mass production techniques, the essence of which is interchangeability of parts. One of the first persons to demonstrate this technique as Eli W. H. Trnevy, who showed approximately 150 years ago that rifles could be assembled from interchangeable parts, each one of which was fabricated in accordance with carefully prescribed procedures of measurement. More recent advances in the science of physical measurement have brought about instruments that make certain measurements automatically, as well as instruments which make measurements more precisely. A third phase in mechanization is the use of mechanical handling techniques 1v Harabi 7. Automaton. Materials are carried by machine from one processing station to another. The conveyor belt is probably the best known example of this phase of mechanization. A fourth phase of mechanization involves the concept of feedback. Feedback merely means the use of the result of a physical measure meant at one stage of a mechanical process to alter or control an operation at an earlier stage of the process. A commonly used example of feedback is the thermostat on an automatic furnace. The thermostat measures the temperature tour at a particular location and feeds the result of this measurement to the controls of the furnace, shutting it off or turning it on. According to the temperature observation, feedback can be accomplished entirely mechanically or with the intervention of human operators in varying degrees. In the furnace example, a man can be both the temperature measuring device and the feedback element. He shovels coal or closes the furnace drafts, depending on whether he is cold or hot. In steel production, it is customary to run analyses on the composition of the melts at various steps along the processing line. A human operator may make the measurements 1/1th mechanical in strum and switch can result in an orally conveyed order to modify a phase of the production process as a result of the measure NT. In modern petroleum refining, the measuring process, the order giving and the resulting control modification can all be accomplished mechanically. A fifth and most recent phase of mechanization is the utilization of advanced and automatic computational techniques. Frequently, the completion of the feedback process requires computations of varying degrees of complexity on the results of a physical measure meant before a proper control order can be determined. Automatic machines which make possible rapid and reliable computations provide extremely important supplements to the feedback process. It is in this area that the striking recent advances have taken place, providing a basis for extensive future developments. Advances in the tools of computation have another important implication. Hitherto, the trend in mechanization has been confined primarily to the processing of physical materials and devices. Automatic computing machines are, on the other hand, concerned 1/1th processing numbers and through them a wide variety of other types of information. The processing of numbers and information is an important operation in many activities other than production lines. Business offices such as banks, insurance companies, and retailing organizations, government agencies, and scientific laboratories are all concerned with processing numbers and information on increasingly larger scales. Hence, this phase of the process of mechanization appears to have applications in many areas other than the computers and production processes. One here, so much mechanization has already taken place. I mentioned earlier that the goal of mechanization is increased productivity, and increased productivity is, I believe, an objective of primary concern to our nation. Although I am not an economist, it is my understanding that the nature of our economic system is such that it must expand in order to remain vigorous and healthy. In an era when the opportunities for geographic expansion are almost nil, the only practicable means of expanding our economic system is through the development of new products or through the development of techniques for producing products more efficiently. Both of these depend on scientific and technological effort, involving continuing emphasis on mechanization in all of its phases. A recent analysis by Dr. Raymond Avell of the National Science Foundation shows that the productivity of our labor force, as a result of scientific and technological effort, has increased at a rate over 2% a year for the past 43 years. His analysis also shows the productivity rate to be accelerating. It was 3% over the past 7 years. The dependence of our increasing productivity on science and technology can be further demonstrated by the fact that approximately half of our labor force is now engaged in producing or marketing materials or devices that were generally unheard of 50 years ago. Progress in science and in industrial productivity are closely related. Advances in each of the major phases of mechanization, which make possible increased productivity, depend on progress in science and engineering. Furthermore, the orderly advancement of science also depends upon developments in some of the same areas that are important to the GR01th of industrial mechanization. 2 ends of measurement is fully as important to general scientific progress as it is to industrial progress. Better instruments and techniques of measurement aid both science and industry. Further advances in the computing machine field will like 1DSE aid both areas. The interrelatedness of science and productivity is demonstrated by the fact that new and improved production methods make possible new and better tools, material and instruments for the scientist, enhancing his opportunities for discovery. I have stressed this interrelatedness because it is important to appreciate that progress in all phases of science and technology contribute to increasing productivity, which is essential to a vigorous economy and a strong nation. An important characteristic of an expanding economy, dealing with new products and new techniques, is that it must be accompanied by an expanding science. NELF problems must be solved which are of /is larger and more complex. It is in coping with such a situation. 8. Automation. That the NEL automatic computing machines assume major significance. Many of the scientific, and technological advances which have been made with the use of these machines would have been either impossible or excessively costly to achieve without them. Modern guided missiles and the hydrogen bomb provide 2 outstanding examples. To date, our experience with these machines shows that they are not used primarily to do old fork with fell rare people. Instead, LFE are tackling the important new problem with the same or even more people, thus increasing our capacity to explore the unknown. Viewed in this light, the recent developments with computing machines help to fulfill the current need of science and technology. Advances have now reached a stage of here further progress would be impracticable or uneconomical without them. The utilization of modern high-speed computing machines has, so far, been mainly in the field of science and technology, especially in those areas important to our defense effort. It is extremely likely, however, that their ultimate major use will be in the field of vice operations for both government and business. In this area, we now find a situation somewhat analogous to the state of scientific technology before the advent of these machines. Office operating problems have reached a size and complexity that can fast become a barrier to further efficiency and growth unless there is provided better means for handling the masses of information which clog modern offices. This situation has been very well described by former Assistant Secretary of Commerce James C. Worthy. I should like to quote from one of his talks. it is a fact of great significance that the number of clerical workers has increased more rapidly than the number of productive workers during the past half-century. Modern productive techniques, with their consequent centralization of direction and control, require increasingly greater proportions of per processing personnel. Unless current trends can be halted or reversed, an ever larger and larger portion of the nation's total manpower will necessarily be absorbed in unproductive record-keeping overhead at the expense of a field creating effort. The technological response to the current challenge is already clearly indicated. The development and refinement of electronic data processing systems offers the same possibility ties to business that it does to science and to government. And the end results can be similar, a greater concentration of available human resources on the production of tangible goods and services and a smaller proportionate loss to non-productive overhead. As in the case of government personnel, this development will not lead to large-scale displacement of employees. The process will computers be gradual and permit ample opportunity for orderly adjustment. Over the long pull, it will result in the gradual diminution of monotonous, repetitive paper handling work. At the same time, it will gradually increase the opportunities for interesting, creative high-skilled technical assignments. The consequence will be not only greater gains but higher human satisfactions and automation. The consequences for management are equally significant. One of management's greatest problems is that of securing adequate and timely information on which to base day-to-day decisions. The complexity of modern business organizations has created chains of common that often isolate the decision-making group at the top from the basic facts which are essential for effective, timely control. Paradoxically, it is also true that top management may be literally lamped with undigested facts and figures too voluminous to use. 1. Of the imported .d.t gains from the new electronic techniques will be the bringing of the right facts to the right people at the right time. Every day, new and divergent facts develop which those in responsible positions in government and industry must carefully consider and analyze. These mountains of data will surely overwhelm us if we continue to follow the practices of those who lived in a simpler time. The electronic computers, with their remarkable ability to assimilate and store information for rapid selection and access, may be a primary factor for sound, wise public and business policies in the troubled years ahead. Our federal government has the largest office operations in the world. Hence, it seems logical that if modern data processing machines have a place in improving the efficiency of large-scale office operations, there should be numerous possible applications WLLH in the federal government. Our experience has shown that this prospect is indeed very good. The Advisory and Consulting Services 0F, the National Bureau of Standards, have led to a need for keeping abreast of all MAJ or DE developments involving data processing and information handling systems. This experience has enabled me to provide a brief summary of the state of the art for its possible to the members of this subcommittee. is included as an appendix to prepared statement. Bureau of the Census. I mentioned earlier that our first ACTI 6TI WITH modern computing machines was IN. Assisting the Bureau of the Census. Census Director Robert W. Burgess has already told you of their experience with computing mock INS, so there is no need for me to discuss that phase of RT fork. There was, however, 9. A related development for Census that should be mentioned briefly. This development involved automatic means for translating the data on the record sheets of census enumerators to a form that could be fed directly into their computing machines. The machine we developed has been named FOSDEC, Film Optical Sensing Device for Input to Computers. The machine reads marks 0n microfilmed copies of documents that have been marked T with an ordinary pencil or pen, and then processes the information into electrical pulses T which are recorded on magnetic tape for direct input to an electronic computer, such as the Census UNIVAC. FOSDEC is designed to reduce the T-lork that is now involved in converting written records into a medium AC, acceptable as input by data processing machines. This is particularly true since FOSDEC allows considerable freedom in design of the documents, and does not require the use of any special writing instrument. It is anticipated that ultimately the use of this machine will reduce appreciably the massive amount of paperwork entailed in summarizing census information on the entire population. Although designed for census operations, FOSDEC may be generally applied to the processing of other types of information that must be handled in large quantities. With the development of many large-scale electronic computers in the past 12 years, there has been an increasing need for equipment meant to bridge the gap between the machines and their sources of information. This is especially true for computing systems which perform relatively little computation on a large mass of data obtained from many sources. Considerable attention has been given to computers and their input-output equipment, but relatively little to pre-input apparatus or instrumentation permitting the computer to have direct contact with sources of information. When human beings are considered as sources of information, only two partially automatic means of communication are in general use. These are, 1. Typet-free ters of various forms, and 2. Special marking instruments such as punches or conductive pencils. An alternate method is through the manual preparation of punched cards. To these methods has now been added FOSDEC, a completely automatic machine which processes marks made by an ordinary pencil or pen into a form directly able by the computer. Patent Office. Another unit of the Department of Commerce. The Patent Office has a particularly challenging problem in the area of possible mechanization of patent search. Our patent SYS TEM is closely related to the industrial GRO WTH and prosperity of the United States. It plays a major role in the creation of new ducts and processes, yet our patent system is computers and at a crossroads because of the very increasing complexity in the continued program of inventiveness. The present patent examiners are as dedicated and competent as their predecessors, but they face a task that is infinitely more complex than that of even a 12 decades back. The unprecedented pace of science and technology is producing new facts and inventions at a rate beyond the capacity for patent and claim handling procedures which have been developed over the years, so that the present staff is unable to keep the size of the backlog of patent applications from steadily increasing. In awareness of this problem, the Senate Appropriations Committee specifically directed the Department of Commerce to make an aggressive investigation of the possibility of mechanizing patent search operations. In accordance with this manuit, a committee, headed by Dr. Vannevar Bush, was appointed. This committee concluded that if the patent system is to continue to make its contribution to our expanding economy, mechanization of the routine aspects of the patent search process is essential, and that the automatic data processing art has reached a stage of development. One which makes feasible its application to this complex problem. Accordingly, the Patent Office and the National Bureau of Standards are cooperating in a joint program of research and development to adapt machine techniques to these patent office operations. Army Quartermaster Arshi-Ork for the Army Quartermaster Corps gave us experience in coping with the problems of government purchase and procurement. In carrying out provisions of the Armed Services Procurement Act of 1947, a number of complications arise in determining the bidder or combination of bidders who will charge the true one-at-st cost to government. True cost ts require consideration of different freight rates from factories to depots. The bidder himself may state restrictive provisions such as minimum and maximum quantities, or block or hinge bids whereby he may quote different prices on different quantities. The attempted resolution of lowest cost for bids on contracts involving a variety of complicating factors, TLHAN carried out by MAN UAL methods, results in high cost both in time and manpower. On one typical operation, 700 man-hours were expended without trying all the possible combinations, and it was estimated that 4,000 man-hours 14/old have been required to calculate all combinations. A second shortcoming of manual computation is that in some cases it is not possible to solve the problem at all in the time available. For example, a proposed contract for 860,000 woolen jackets to be fabricated for 13 different destinations, estimated to involve 223,000 different combinations, had to be cancelled because bids could not be evaluated by manual computations. Automation. Accordingly, a program was established at NBS to explore the use of new mathematical techniques, called linear programming, in conjunction with the use of high-speed electronic computing equipment for the evaluation of such complicated bid patterns. The linear programming computation procedure, as coded for SEAC, is then used with data on the various bids received for each specific problem, and the machine operates on the specific problem by first assuming that an advard satisfying the various restrictions TDLL be chosen regardless of its cost. A cheaper allocation is the N sought, and it is substituted for the first. The search for still cheaper allocations continues until no cheaper award can be found. For the typical problem, about 2 hours of SEAC computation are required before the minimum cost in STFR is found. The direct savings achieved through the Speed of electronic computation can be illustrated by the fact that, for a problem that would have required 1,000 man-hours of labor, at a cost for manual computation of approximately $2,500, the machine could have tried all combinations in about 40 minutes at a cost of $80 or less. Direct savings are also achieved through the saving of time, since bidders may limit the effective period of their bids to option pari ds of 20 days or less from the date of opening bids. In summary, then, the linear programming technique makes possible the development of solutions to bid evaluation problems in less time, at less cost, and with absolute accuracy. Veterans Administration. In an application elsewhere in government, the Veterans Administration has used computers for work in relation to actuarial tables. In this case, the David Taylor Model Basins UNIVAC system is used to provide the actuarial tables necessary for the NELF Uniformed Services Survivors Benefit Program. Using conventional methods by desk calculation, this would have required an estimated 25,000 man-hours. The job actually took 1,443 man-hours. The cost by conventional means would have been in the neighborhood of $200,000, if TFAS actually completed for about $15,000 TDTH. The UNIVAC. In the course of the entire job, the UNIVAC computed 357,012 numbers to 8 significant figures. The 1,443 man-hours used on the problem included time spent in analysis and process charting, FLOTLCHRTing, coding, preparing desk calculated samples for checking, preparation for an operation of the machine, report writing, hand editing, and check-in tables, and maintenance. The actual time spent by the UNIVAC in generating the numbers, not including checking of programs, loss 41.4 hours. The total time used by the computer system 1 as 104 hours. As a comparative figure, a FELF sample values 10 computers and computed by hand for checking purposes required 55 man-hours. More significantly, however, the Congress directed that this veterans insurance program should go into effect within 60 days from the time that the Act L/1 is signed. The use of TE computer made it possible to provide the SRE table so that the program did go into effect on Schedule L with maximum benefit to all concerned, something that would have been possible without the use of these new general purpose, high-speed tools. Navy Aviation Supply Office. The Bureau has also assisted the Navy in applying automatic techniques to its invento, control and supply problems. The data processing application that is now in operation at the Navy's Aviation Supply Office is a good example of better use of present resources. In the Navy supply system, there are some 13 material control centers, called supply-demand control points. These control points have cognizance over certain broad categories of material. In the case of the Aviation Supply Office, the responsibility is for aircraft engines, and supporting spare parts and accessories. The supply replenishment actions used to be based on quarterly distribution and procurement in Accordance LDTH predicted demand determined by existing inventories and demand for a previous quarter. Under this control system, the regular quarterly actions had frequently to be supple meant by special actions prior to the next scheduled distribution in order to take care of fluctuations in actual demands. In S0ME cases, as many as 40% or more 0F the stock transactions were interim transacti 0NS, reflecting such unanticipated demands. In an attempt to improve the control SYS TEM, the program usage replenishment SYSTEM PURS technique was developed in the hope 0F, attaining a more realistic balance between inventory levels and projected requirement based upon program plans. However, the introduction of this system for a few classes of supply items materially added to the computed IONA 1 workload at ASO. To extend the PURS procedure to additional classes of material required an even greater workload, it was therefore reasonable to look toward the adoption of electronic data PROC ESNG techniques as a way of accomplishing this mission more expeditiously and more economically. The data processing equipment that has been installed, the IBM 701 and 702, is now working on this job, so that management may more effectively control the procurement and distribution of supplies to meet requirements. Air Materiel Command. The Air Force has had problems of computation for mobilization planning and for logistics control similar to that of the Navy's ASO. The Air Materiel Command is now using and actively exploring the further use of computers for logistics management. One of the problems automation they face is the development of a system L/Hitch C and be expanded during an emergency with H0UT, requiring a greatly increased staff. The Burp has assisted the Air Force in Ilias program. In the first instance, the Bureau assisted in the selection and procurement of their first automatic processor for the Office of Air Comptroller. In the second instance, we are helping to assist the Air Materiel Command in training their supply and logistics personnel at various bases. The interesting aspect about this program is that GS4 and GS5 stock clerks are being given an opportunity to learn to carry out some of the programming operations for the computer. I have reports that they are doing QTE well. I might mention here that the Burp has not had considerable experience in training personnel to operate automatic electronic devices of this sort. I think it is one of the important VPLUs of our central computational and data processing staff. Public Housing Administration. The experience of the Public Housing Administration provides an example of H01 VM0 REF. Effective work can be done with the use of data processing machines. In the low-rent housing program administered by the FA, it is necessary to determine eligibility for continued OCCU PANSI by auditing INCO and other statistical data concerning the tenants with their present staff. This can be done only on a SAMP1 basis. As the result of an experimental trial of this audit task on SEAC, it was assumed that a 100% audit would be possible tvith the same staff. In addition, the procedure can be organized so that their staff would be able to give more attention to borderline cases where careful, human judgment is required. Future activities. The preceding examples do not provide complete PyTour, but I hope they have served to demonstrate some of the advantages T0BE derived from applying modern data processing techniques to government operation. The are, in fact, a host of applications which are now in the planning stage or, in an even greater number of cases, still uncontemplated. In recognition of the demand for BRAU services in this field and for the increasing use of automatic devices for government operations, the National Bureau of Standards has requested and received initial appropriations from the Congress for the construction of a pilot data processing system. This pilot's turn is now in the planning stage and will take about 2 more years to get into operation. It will provide government with a NTRA1 facility for studying on a sample basis, as in the case of the housing report, the feasibility of various automatic systems and components for use in organizing procedures so that automatic machines can serve the particular needs of government agencies. Since this pilot facility must be adaptable for actual sample trial runs of contemplated systems for a large content on page 38. 11. Tape identification and rerun procedures for tape data processing systems. Leonard Eelson, Remington Rand Univac, New York, NY. Over the past few years the size and complexity of digital computers have greatly increased. Even the so-called small computers of today are in many ways far more complex than the most advanced computing equipment available 10 years ago. From an Econ 0 MIC viewpoint, modern large-scale data processing systems have fully justified their use in many areas of application. Many functions previously impossible are now performed daily and routinely. Other functions are now performed at a far lower cost with greater speed accuracy than previously possible. A comparison of data processing systems of today with those of 10 years ago reveals the following differences. 1. The number of pieces of equipment has been materially reduced. 2. The complexity of an individual piece of equipment has been increased. 3. The number of people required for the data processing system to function has been reduced. 4. Many of the routine decisions were previously made by PERS 0 North Northeast 1. RNOI / made by machines. Any system involving people or machines is subject to breakdown and error. In the past, because of the many diffuse error varied elements in the system, it was not in general practical to rigorously systematize the procedures to be followed in the detection and correction of errors. Modern tape data processing systems do not suffer from this disadvantage because of the relatively high costs involved in the operation of an electronic computer and because information in the data processing system is all funneled through one piece of equipment. Users of digital computers need to provide efficient methods dealing with errors if they are to get the most use out of their equipment. If they don't do this, long delays and heavy costs in the processing of data can bet consequences. The subject can be broken down into TT\0 phases: detection of errors and the correction of errors. We shall first consider the detection of errors. There are two possible sources of errors. 1. Failure of personnel to properly FO11 if predetermined procedures, and 2. Equipment failure. Most data processing operations involve large files of data which are stored on magnetic tapes. These tapes generally bear labels which identify their contents, for example, MOS-TER. Policy file, September 18, 1955, real number 69. During a run, it is one of the functions of the machine operators to mount the RLS of input tapes on the appropriate tape mechanism at the proper time. In addition, the operators are required to dismount the output reels and affix the correct tape label to the reel. 1. Is by no means assured that these operati 0ns will be correctly executed every time. Another type of error which may arise is as follows: during the reading of information into the computer, a particle of dirt, or perhaps a transient error in the read circuits, may cause the information to be incorrectly transferred into the computer. This condition is detected by checking circuits in most computers today, and often a reread of the information is automatically attempted by the computer. However, if this procedure fails, the operator will attempt to repeat the read instruction from the control console after taking GSUCH measures as cleaning the reading head. In this process, he is required to backspace the tape before each attempt. One is not assured that he will do this, or that he will not reverse the tape twice. Thus, there is a possibility that a block of information may be bypassed or read twice. These are typical errors that can be made by personnel operating the computer. The second source of error, ARISES from equipment failure, falls into two categories. IES. These are the transient failure WICH occurs erratically with a mean error-free time anywhere from half a minute to several hours, and the permanent error, which comes into play during a large percentage of the time that a particular circuit element is used. The F0R mere of these, the transient error, is ILDLCHMAR. Difficulty to detect and therefore much M0RE likely to propagate through the system. Most modern computers are equipped to suit _extent TDTH checking circuits. These may vary from marginal checking of information transf 12 COMJUTERS to complete checking circuits which will detect virtually all errors. Those computers which are not self-checked should have their programs include checking calculations. The nature of the checks program TDLL depend upon the type of checks provided by the hardware and automation. Some errors, whether detected by the computer checking circuits or by programmed routines, will be corrected immediately. These are not of interest here. Other errors will necessitate going back in the program or perhaps to a previous program in the system. One latter case arises, for example, when an input tape proves to be unreadable. In computers today, it is possible to monitor and check information going on a tape to the PNNT, where it reaches the right heads of the tape mechanism. IIOL such conditions as an undetected bad spot on the tape or the presence of dust or dirt can cause the information to be improperly recorded, making it impossible to read in future runs. At this point, it should be noted that errors are not the only possible interruptions of a data processing run. Sometimes, it is necessary to remove a problem to make way for one of higher priority, or a special run is to be ticked in regularly scheduled runs. These problems are logically equivalent to the case of an error interrupting normal computer operation. We will now consider a general rerun procedure and an associated tape identification scheme. These combined techniques may be used to restart problems. Due to the large number of reels of tape usually present at a computer installation, it is necessary that each of the reels containing information bear an identifying label. HAL.VEVR labels are not a solution to the problem of identifying reels. In the first place, the labels are created by the machine operator and therefore may be in error. Secondly, the labels may come off the tape because of mishandling. It is therefore necessary to record an identification block as the first information written on a tape. This identification block should contain all the information which normally appears on the tape labels. In addition to providing a more permanent record of the contents of a reel of tape, the identification block also permits the computer to check on the manual operation of mounting tapes. Before the computer run starts processing the data on a tape, a check is made to compare the information in the identification block against the expected codes. If the information does not match, suitable outs can inform the operator of the necessary corrective measures to be taken. 13. The check to deter whether the operator has skipped or duplicated a block of information is carried out as follows. Each time an output tape is produced, the programmed routine counts the number of blocks recorded on the tape. This total is recorded at the end of the data. When the tape is read into the computer in subsequent runs, a count is made of the number of blocks read. At the end of the tape, a comparison is made between the number of blocks read and the number read. 10. If the totals do not match, a rerun is initiated. Thus, we see that the computer can be used to check on the accuracy with which the manual operations in a data processing system have been executed. The method of rerunning a problem is very simple. During the running of a problem, the following variables are of significance. 1. The contents of the computer memory. 2. The identification of the various tapes on the tape mechanism. 3. The block counts of the various tapes in process. In order to rerun, it is necessary to know only those three things. If at the end of each output tape in a run the contents of the memory are written out, a rerun point is established. If necessary, the contents of the registers may also be recorded at this time. Note that the block counts and tape identifications are being stored in the MERN for reasons mentioned previously, and therefore, all the necessary information for rerun is in the memory dump. The procedure for rerunning is as follows. When an error is detected, the last output tape produced is mounted on a tape mechanism. A simple row time locates the memory dump at the end of the tape, thereby reconstituting the computer MEM. ORI. The tape identifications of the various input and output tapes are now available in the memory. They are printed out for the operator and he proceeds to mount the tapes. These tapes are then repositioned making use of the block counts which are stored. This rerun procedure is general and applicable to most data processing runs. For large computers, writing out the computer memory takes less than 2 seconds and uses less than 1% of the available storage on a reel. For mathematical problems, a similar rerun procedure may be set up. A rerun point is established in the same manner. Rerun points can be established at fixed positions in one program or by operator intervention at frequent time intervals. ENN. Conference on Electronic Digital Computers and Information Processing, Darmstadt, Germany. October 25 to 27, 1955, Titles and Abstracts of Papers. A conference on electronic digital computers and information processing took place at Darmstadt, Germany, October 25 to 27, 1955, at the invitation of the Institute für Praktische Mathematik, Technische Hochschule, Darmstadt, as expressed by Dr. A. Walther, conference chairman. Following are the titles and English abstracts of the 60 papers, not including those given just after the end of the conference by the two speakers from the USSR, Lebedev and Basilevsky TWLOSE. Arrival was delayed. See Digital Computers in Eastern Europe in Computers and Automation. December 1954, p. 8-9. At the end of the titles and abstracts is the list of speakers and addresses. It is expected that the papers will be published in Proceedings. Available from the IPM, Darmstadt. 1A Adam, Lin/Österreich. Statistical Operation Programs in Industry. Tile possibility to use computers for the purposes of production research necessarily leads to a corresponding reorganization of Manage M8NT. Therefore, the development of standard operation programs to be used again and again in the factory is deemed to be an essential preparatory W0RK. Then it would be evident that the use of a computer is suitable. ENVO examples are mentioned. Further, the author demonstrates in which way production research has to be organized in order to justify the use of computers even for special purposes. To Rio Aiken, Cambridge, Mass/USA. The Future of Automatic Computing Machinery. Story of the subject. What has been accomplished? Where are we going? Hotelville we AC. Compelish, A. Applications to data processing and B. Applications to automatic control. What will be the effect on society? What is the responsibility of A. Computer experts, B. Engineers, and C. Educational institutions? Conclusion: we are building a new branch of engineering. 3K2 I3 Ekman, Dresden. Specific characters of the Dresden Computer 01. Abstract not available. 4FLI3 Hour, Mgen. Iterative methods of linear algebra with convergence of I3 Bernoullis and of G-ray F phase. Type. Iterative processes of linear algebra are T0. B of Bernoulli's type if their linear converge ins depends on the final preponderance 0F0 Ne. Term in a weighted power sum of matrix eigenvalue. Prototypes are the vector iteration for determining ing the eigenvector belonging to the domain ant. 14. Eigenvalue and more generally a process NAMED. Staircase iteration for simultaneously determine ing all eigenvectors and eigenvalues of a matrix X. The latter case being closely related to RUTIS. Hauser's LR transformation. If an iterative process of Bernoulli STYPE is accelerated in such a way that the two 1th iteration quantities are used, one obtains quadratic convergence, which may be called of G-ray F phase type. A number of important numerical procedures are contained within the staircase iteration and the vector iteration, or in their quadratically convergent abbreviations, as special cases. They are to be studied with respect to their mathematical relationships. Special interest is given to the phenomena of self-correction on the one side, instability and loss of leading figures 0 and the other side, which are significant in numerical computations, especially with automatic machinery. 5v Belovich, Brussels/Belgian. Handling of numbers and orders in the IRCA. FNRS computer. The words used for programming are numbers of 18 binary tetrades, 15 decimal numbers, 2 decimal numbers for the exponent and 1 for the sign. The orders have the length of a half word. The computer is of the single address type, the resultee of the last operation remaining in the accumulator. The orders are composed of an address indication, possibly indication of another order in KI of jump orders, and an operation symbol. The selection and interpretation of orders on one hand, the selection of numbers on the other hand, and finally, the calculation itself are desynchronized. Information processing is handled over a cold cathode tube ionomery, which allows a maximum frequency Y0F 25 kc/s for circulation of the tetrades. His corresponds to the relaxation time of 40 FOS of the switching matrices of the arithmetic unit USIN-G. Selenium rectifiers. The author describes the systematic of pools, ing and gating circuits used to combine the orders corresponding to different operations TV at H. The characteristic instance at input and out PUT0F. The matrices. Hereby a fine structure of timing. TV thin 40 RS is established. 6L Bierman, Göttingen. Survey on the computer development at Göttingen. Especially the application of the computers. GL and G2. Abstract not available. 7.2. Billing, Göttingen. Switching circuits and memory systems. Computers and automation. Main characteristics for the design of STDTCH. ing circuits are according to their import and CE. Reliability, easy maintenance, speed, costs. From this point of view, the most important E1 ERN NTS. Tubes, diodes, ferrite CFRRES, transistors, array. Compared. Special requirements for these components in flip-flop and gating circuits are discussed. Because of their reliability, ferrite cores and diodes are increasingly used instead of tubes in ring counting circuits, shift registers, parallel registers, and logical elements in the arithmetic unit. A simple logic design of the control unit may be achieved by microprogramming techniques. Able circuits with ferrite core matrices or ferrite registers are compared. These switching circuits are assembled to plug in nits if possible. Ferrite core matrices are increasingly used for rapid access memories. Some selection circuits are compared. Large capacity magnetic tape memo. RISE, above 10.8 binary DGTS, T.11 ITH maximum access. Time of FETT seconds have been used in USA. 8 AD Booth, London/England. Input and output. The various forms of available input OUT put. Equipment for automatic computing devices will be Revitide. Their suitability for attachment to cool computers which employ currently available storage devices will be discussed, and the methods by which accurate dovetailing of the computer and its terminal organs can be achieved will be discussed. Research at present in progress on net forms 0F. Input-output equipment will be discussed, TVITH. Particular reference to magnetic tape and TVIR. And to devices for the direct use of 0Regina 1. Documents. 9H Baten-Bruch, Darmstadt. Subroutines for DERA. The author discusses characteristics of SUB. Routine organization caused by punched card tech. Neeks and Adressenreichenwerk, Special ARITH. Medic unit for address modification. By means of punched card technique it is possible to perform changes of the first kind, substitution of relative addresses, before program sequence input. Changes of the second kind may be performed by means of Adressenreichenwerk. The methods AP applied in Darmstadt and München are COM-PARED. Insertion of short subroutines as open subroutines into the main program will be discussed. 10K Brocade, Sindelfingen. Address modification tilth index registers used in EIFM type 704. Description of type 704 index registers in their operation. Decrement modification of address into effective address, index arithmetic. Index-dependent routines, selection of complete subroutine supplements. 11 St. Comet, Stockholm. Schweden. Operation with BESK. BESK is an electronic parallel computer ITH. Cathode ray tubes as rapid access memory. The words are handled to and from the memory in a parallel mode. Words signify numbers in the arithmetic unit and orders in the control unit. A magnetic drum is used as supplementary memo RY. 15. Input of program and numerical values by me and S. A punched tape. Output by means of E1 ECT rig. Typewriters or tape perforators or graphically on a so-called function recorder. The AUTH0 Arda describes in his paper the order list. Since March 1, 1954, BESK is in Regu 1AR operation. A survey is given of different probe lems resolved with BESK and some details are discussed. Programming of problems is now mostly worked out by the users themselves. Programming courses are arranged by our mathematicians who he 1p the users if necessary. Mainly they are occupied with preparing a library of standard subroutines, which are described 12 EWDIJK Amsterdam, Nederland. Iterative processes for the computatio and 0F. Elementary functions. Iterative processes for the calculation of the square root and the reciprocal are adapted TAA. Fixed point binary machine, range from -1 up to +d. W without a built-in division. The adaptation IN includes a solution of the scaling problem involved, ensuring no loss of accuracy. A fairly good AP approximation, to be used as starting value, can easily be constructed. 13 H.J. Dreer, Darmstadt. The Darmstadt Electronic Computer Dera. Emphasis of the development, to build a mock INE of medium speed suitable for long programs as well as for input and output of great amount of informati 0n. Convenient handling, release of the arithmetical unit from auxiliary computati an of programs. Careful design with simple RLIAB1A units. Representation of numbers and orders 0 and the basis of binary coded, serial decimal figures. Special features in the main units, ARITH. Medical unit, store, control, input, and output. State of the development. 14.0 Eckert, Lauf. Critical view of ferrites with rectangular R. Hysteresis loop for application as memory. Or switching elements in electronic digital computers. Designing physicists and manufacturers of ferrites with rectangular hysteresis loop for apply cation as memory or switching elements HAVito. Know some test methods allowing a quick classify cation of the cores. These methods are discussed shortly, taking up the hysteresis loop at differ and frequencies, the NVE lop E method DE. Termination of switching times and of the noise to signal ratio. The analysis of the hysteresis loops of these ferrites taken up statically, quas statically or WITH high frequency of 100 kc/s. Can deliver only excluding classifications. It replaces by no means the pulse test. Only his test gives statements on switching time and on the noise to signal RDTIO. Steemag has developed a method based on billing selection test HL/H2. Loading the codes with a sequence of pulses C on computers and continuously modified in amplitude and in ZR10-9. AP01 Erfel reading pulse, which pulls the co-RE back to BR. This test makes visible a group of output pulses on the CRT screen. Its envelop allows to define instantly the core's useful range of operation. Then something I will be said about opposite tendencies of development in the United States and in Europe. 15th. From, while the representation of the structure and the function of digital information processing machines by the equivalence algebra. For the description of ReLa Y circuits Shan, Non, Plekel, Zis and others have developed the switching algebra, which is based on the formalism of Boolean algebra. The latter can be modified and extended on many valued variables, if the n Gaussian and the axiom 1, x equals 1 are replaced by the equivalence operation xy defined by xy equals 1 if x equals y, xy equals 0 if x plus y for every discrete valued variable. The FAL 101 FING problems can be treated t-hor-oofly by a kind of tensor formalism. 1. The representation of states, and of sequences of states in a communication system by variables and equations of the equivalence algebra. 2. The general theory of systems of equations and their solutions. 3. The extension of the algebra by a precisely defined transport symbol A plus B becomes formally identical with the Planck-Alnel algebra of programs. Special has been attached to precise definitions of the basic notions of communication theory and of the relations between algebraic symbols and the physical variables of technical communication systems. An example shows the description of a machine of the minima type by the formalism. 16 H.G. Eilert, Darmstadt. Something on switching circuit techniques with ferrite toroids. There will be shown swap possibilities to form logical operations tvith magnetic cores. By giving examples there will be made statements on projecting, designing, and constructing of switching circuits. 17H2. Goldston, Princeton, N.J. Systematics of Automatic Electronic Computers. The speaker considers historically the interrelationship between the logical structure and speeds and capacities of electronic digital machines. Using this as a starting point, he next cedes to a discussion of the mathematical desiderata of machines viewed in the light of present-day mathematical interests. On the basis of these C0n side rations he attempts to establish the speeds and capacities desired for machines in the foreseeable future. He then proceeds to see how these speeds and capacities can be achieved and wherein the principal difficulties lie. 18H. Goldston, Princeton, N.J. Numerical procedures for the integration of hyperbolic and elliptic partial difference equations. The AUT or discusses two main topics, the integration by various numerical methods of 16. Automation. Perl partial difference equations, and the corresponding situation in the case of elliptio partial difference equations. In the case of hyperbolic ones he states the so-called current T. Friedrichs-Louis criterion for stability and discusses generally the relation between stability, convergence and accuracy. He gives a number 0f explicit integration procedures and an implicit 1. In the discussion of the latter method he develops for difference equations a theory of the Green's function and shows its applicability in the present circumstances. In considering elliptic equations he discusses the work of Frankel and Young principally. His main interest in this calculation is the different notions of over-relaxation, and he shows the rate of convergence of these methods. 19 G.B. Green, Oakland, California. Data processing. Abstract not available. 20 W. Hansen, Haslow. Numerical solution of differential equations. In hydrodynamics with BESK. Hydrodynamic differential equations of flow. In the sea and in rivers. Conversion into non-linear difference equations and solution by numerical methods. Influence of terms characterizing friction and convection on the stability of the solutions, stability criteria. Application of these methods for numerical solution of practical problems of hydrography and hydraulic engineering with BESK. 21 K. Harold, Nuremberg. Ferrites and Titanats used for decision elements in switching circuits and memory systems. The recent development of materials has won ED, especially in the field of ferromagnetics and ferroelectrics, to a great number of net component and thus opened for circuit techniques SOILE. Interesting possibilities of realization. Based on the well-known facts for modification of physical qualities of these materials by external fields, control of field density, Faraday effect, Hall effect etc., it shall be examined to which degree components on this base are already used in switching circuits and memory systems of electronic computers. Further it shall be examined which possibilities are given by Userg. New experiences resulting from research 0 and FER. Rights and Titanats especially with view to reduction of tubes and miniaturization. By means of pictures the author shows constructive details of components and their arrangement in different switching circuits and memory systems. 22 W. Hoffman, G. Trinzenair. Remarks on the development of G-Law. Based on construction principles of G1 the Arbeitsgruppe Nummerischen Maschinen develops. At present G-Law input of orders immediately carried out by punched tape sensing device operat. ing. Above 100 line/section. Magnetic drum memory. With 1840 numbers, each number 60 binary digits. Arithmetic unity in binary number SYSTEM-TVITH. Floating point operation. 13 decimals for man. TISA, maximum decimal exponent 37. Computing. Computers. ILETH double accuracy or fixed point operation, also. Combined, possible by programmed orders. Replace. Meant of address substitution by cyclic interchange. Over maximum 60 numbers of each track and free. Assignment of tracks to the third address number. Conditional jump orders dependent on sign of man. TISA or exponent or special marking of numbers. Average operating speed approximately 15 to -20. Operation/sector 10 punched tape sensing devices. For input of orders and numbers. Output on punched tape or with electric typewriter. Keyboard 0F. Typewriter may be used for direct input and control. Used components, CA250 tubes and more than 1000 diodes. 23 AS Householder, Oak Ridge, Tennessee. Numerical mathematics from the viewpoint of electronic digital computers. A computing system it her or not it includes. A human being can be characterized by a list of elementary operations with a reluctance factor. A. Associated with each operation. The reluctance factor may be a measure of the time required for the performance of that operation. We can say that numerical mathematics is concerned with the construction of routines with minimal total reluctance for specified systems and which yet satisfy assigned criteria as to precision. When the SYS-TEM includes a human being and only minimal mechanical facilities, a routine can be modified at any stage. When the system in an electronic computer operating at high speeds, this is no LOLIJ possible, or much less so. Because of this fact, the MOJ, or change in view point imposed on numerical mathematics by TILE electronic digital computer lies in this, that precision can no longer be taken casually but must be carefully scrutinized in each routine. Probabilistic estimates are open to question because of the obvious fact that some numbers such as the simple rationals, transcendentals such as E and RR, and others will bias distribution in Mr. Iaslavas. Very few systematic techniques are available for analyzing computational errors. Nevertheless, a few can be cited having some degree of general IT. A certain algorithm for computing 1/10 roots of a symmetric matrix illustrates a principle that seems to be new and that may prove to be useful in other situations. 24 P. Klein, Fellbach. Special requirements for oscillographs to be used for development, testing, and monitoring of electronic computers. Abstract not available in English. 25 H. Kohler, Sindelfingen. EDPM 705 in Engineering and Management. Units composing Type 705. Operation possible. IDAs of each unit. Interactive process of diff. Ferrant units. Daily stock control, also in case of largest. And decentralized stocks, by means of 705. Sorting of data on magnetic tapes. Obtainable. Sorting speed. I. 26T Letterla, Heidelberg. Numerical computation of star ephemerides. Spherical coordinates of fixed stars are vari. And automation. Able TVITH time on account of 1. The transformation of the reference system owing to precession. And nutation, 2. The aberration of light, 3. The real, proper, motion of the stars. The calculation of the apparent coordinates, as actually observed, may be reduced to a simple formula consisting of the sum of 5 products. The first factors depend only on the position of the star, while the second factors are common for all stars and depend only on time. The Astronomisches Recheninstitut at Heidelberg Wheelie compute, as from 1960, the spherical coordinates of all 1483 so-called fundamental stars which define the astronomical coordinate system. These ephemerides, given at an interval of 10 sidereal days, are published annually in an international volume apparent places of fundamental stars. Each volume contains approximately 60,000 positions or 120,000 coordinate values. Consideration has been given to the most economical method of making these calculations. The use of punched card machines seems to be advantageous because it is possible to produce copy on an IBM card-controlled Type L1 triter in a form immediately suitable for photolithographic reproduction. 27 N. J. Lehman, Dresden. Present status and trends of the Dresden computer development. Abstract not available. 28 N. J. Lehman, Dresden. Remarks on automatic computer programming. Abstract not available. 29 H. O. Lilac, Emchen. Physical problems of the construction of recording heads for digital magnetic drum storage. In the development work on the magnetic heme for the drum storage of the PL, it has been systematically investigated as to what quantities are important in influencing the L forking of a magnetic head in the digital recording on a drum. As are well known, the TLVO main requirements are high resolution and good energy efficiency. For the resolution, the geometrical shape of the pole shoes and the separation between the magnetic layer and the head are the important influencing factors. The result of theoretical as well experimental investigations show that the nowadays commonly used construction of the magnetic head out of one or more laminations with small pole shoes is much more suitable for the drum storage than the type of pole shoes used in magnetic tape recorders. The required magnitude of the recording sig. NAL and the voltage amplitude obtained in the read out are dependent on the shape of the pole shoes, the layer head separation and the layer material. By regarding the head as a non-ideal energy converter, an equivalent circuit diagram is derived. Illustrates how the signal energy transfer one's influenced by the resistance of the windings, the magnetic reluctance of the core and the extent of the stray flux. 7. Computers and technical possibilities for reducing the causes of attenuation are discussed. By adopting these measures in the construction of the magnetic heads for the PERM, a high storage density and a relatively small amount of required amplification have been achieved. 30G laser, Mchan. Magnetic Sloaching Circuit Technique. Abstract not available. 31M Linsman, W. Pouliart, Antlier Pen/Belgian. Main characteristics of IRCIA FNRS computer. Survey on the logical, mathematical, and technical characteristics of the computer, use of cold cathode clot discharge tubes for storage, DYN. Cronus operation, unification of calculating on 1TS etc., statement of reasons determining TS. Choice. 32BJ Lupstra, Amsterdam/Nederland. Processing of formulas by machines. Some of the methods that could be used for it present-day machines to make them understand the language of mathematics are discussed and disadvantages of these schemes are summarized. The problems connected with the elimination of unintended redundancy from the coding are mentioned. Some suggestions are given for the incorporation of more of the machine's understanding into its hardware and less into the program, with the aim of obtaining better overall efficiency. Some preliminary conclusions about the DevSecOps logical structure of the machine in this case are presented. The question of reliability versus amount of equipment is mentioned. 33W.H. Muller, Amsterdam Schiphol/Nederland. An electronic computer enters an airplane FAC. Tory. Before the arrival of our magnetic drum calculator, TVE used matrix methods for our computations. On desk calculators whenever possible. After that, we continued this practice. We reduced vibration and flutter problems and also the solution of a system of linear simultaneous differential equations with constant coefficients to the determination of eigenvalues and eigenvectors of matrices. Vibration problems give rise to matrices with Z elements and real eigenvalues, flutter problems M matrices with complex elements and EI.genvalues. For both cases we programmed the iteration method, by which the eigenvalue LDTH, the largest modulus, and its eigenvectors are found. After that, from the matrix 0 WITH eigenvalues T, \y\I, written in descending order of magnitude of the moduli, a matrix 0, is constructed. 0 and 0, HA. The same eigenvectors and both have the eigenvalues. I but 0, has the eigenvalue 0 ins 1 ECD of, so that -2 is the eigenvalue of 0, 2 ITH. The largest modulus. In this L11 I life are able to find all eigenvalues of 0 by this reduction process. Extensions of the program are necessary when two eigenvalues are close together, or when, as in the third problem, a matrix 4 th real E1 ments may have conjugate gate complex eigenvalues. Then a quadratic equation is constructed from 3. 18. Automation. Consecutive iteration steps. The sole outlines of this equation give new approximations to the two eigenvalues with the largest module, e.g. to the two conjugate complex eigenvalues in the last mentioned case. With the aid of these solutions an LFAP approximation to the eigenvector is constructed. When the matrix has real elements, the eigenvector may be real or complex. The program must be able to switch to either case. In the second case, the two conjugate complex ROITs are annihilated at the same time, so that in the reduction process only real numbers appear. When the matrix has complex elements, this complication does not arise. but the construction and solution of the quadratic equation with complex coefficients have to be done with a floating decimal point routine. 2234. H. Ullman, Göttingen. Report on completion of G2. The author characterizes the computer G2 and shows its special properties as number representation, normalization order for facilitation of floating point operation, tape orders for modify cations during input, special orders for neat ta blueprinting, conditional jumps with multiple dependencies of decision possibilities, input of numbers and orders in decimal or octal mode, sep AutoIt storage of numbers and orders on DRUMIS. Deemed to be disadvantageous, nevertheless it is maintained. 35-1/H. München. Survey on the computer development in Munich. Abstract not available. 36 Arpelodi, Mchen. Observations on the problem of data processing. The usefulness of today's conventional PR0 gram-controlled computers for data processing, OP, appears to be doubtful. For these applications, they are clumsy to program and unnecessarily slow, while for scientific computation their value is proven. Therefore, it seems worthwhile to inquire about the essential difference between data processing and scientific computing. The main difference seems to residential IDEIN that an appreciable proportion of a OP problem consists functionally in the task to identify automatically input data on the basis of coded marks which they bear. A second difference arises from the fact that a OP system is usually subjected to different and more stringent operational requirements idth regard to timing of operations, input and output organization, maneuverability etc. 1. Has to differentiate between real-time and deadline, centralized and decentralized operation. These circumstances lead necessarily in addition to the multi-purpose machine to the special purpose system, which latter is built more or less fixed into an organization. Future multipurpose machines will have to be better adapted to the fast and easy solution of the identifying problem with regard to their structure as well to their programming technique. Since some of the most urgent OP problems cannot be solved satisfactorily without a special purpose machine, their development cannot be avoided. Their future significance will depend largely computers and on the development of suitable building block TEMS and short access mass storage equipment. 37K Pisola, G. Tringen. Further development of instruction code of G2. After having put into operation G2 based on first experiences in coding, searching, and correcting of program errors and in real computing, it seems to be desirable to modify and ameliorate the instruction code and the arrangement of PRJNTED numbers. These modifications have been carried out as far as technical construction allowed. It is SHOL1N if here these modifications have reduced TM susceptibility to error of the code and other proposals are made, not yet realized in case of Göttingen computers, which eventually might lead to further reduction of the susceptibility to error. 38 W. L. van der Poel, Leidschendam v. Nederland. The essential types of instructions in an AMATIC computer: multiplication, division, extraction, shifting are not necessary in a computer. Addition, subtraction, transfer, jump, conditional jump are efficient. Of these, addition or subtraction can be eliminated. Conditional jump can be programmed in terms of addition, transfer and jump. A net type of order is discussed, which allol vs addition and transfer. Finally, jump is redundant too. 39 WE Proebster, Mchan. Floating point decimal binary conversion. In the development T10RK of the Perm, 1 Pro. BLEM is the conversion of decimal numbers, of the form PD and C10, into their binary equivalents, UE6, T2, at the input, and conversely at the output. Starting from given arithmetic rules, reasons for the most important fundamental decisions for the technical realization are given, and the plot diagrams for the two conversion processes are discussed. The various arrangements provided for the discrimination of the signs of the exponent and mantissa are described in detail. Finally, in order to illustrate the switching technique used, the author describes the basic CIR quit on TH. The construction of the resulting control unit in the Perm was based 40 C. Ross, Dayton, Ohio/USN. Interpolation trends for large-scale computers. Abstract not available. 41 H. Rudishoser, Z. Rich/Schweitz. Report on 5 years of programming work WITH the Z4 computer. During 5 years of operation in the Institute for Applied Mathematics of N, the Z4 has rendered good services to the Swiss industry, more by the solution of numerous small problems than by working on monster problems. For this reason the program preparation, which is relatively extensive especially for smaller problems, lies our main burden. Therefore we tried to simplify programming and handling of the ERLITH to be built, whilst less attention was paid to computing speed. 19. Automation. As further means for simplification of program preparation, the several well-known methods of programming are at our disposal: flow diagram, subroutine library, conversion routines, etc., which when be used for ERT in a routified manner. The most effective means is, however, automatic programming. By this we mean methods for automatic computing of the whole program according to basic formulas. For this purpose the problems have to be formulated in a special algorithm. For the multiplication of a n with a m p matrix, the spelling is as follows: lot ls m for I 1 1 NAND k equals 1 1 p q.2 tjlci d equals I0. The term to be calculated is always to the right of. It is said that such a strict formulation, which might also be extended to more complicated systems, would also simplify conventional programming. Therefore it may be proposed generally to use this formulation for all numerical problems. 42 K. Samuelson, Mdinchan. Problems of Programming Techniques. The steady progress of programming techniques is increasing the tendency of taking the load of routine programming work off the programmer. The first, still incomplete step in this direction is the preparation of a supply of library routines, which sometimes are stored in wired form unless there are directly wired-in routines, Z4, square root. Such a subroutine NLI is related to more than one operand address and therefore may be called a multi-address pseudo-order. Establishing and entering these addresses Main's the problem for the programmer. On the next level, a complete computing program is manufactured by a master program, executable routine, superplan, prepared especially for this purpose from library subroutines and added instructions, regular machine orders as well as other pseudo orders which are not contained in the operation code of the computer. Some of the most important activities of these master routines are basically of so simple a kind that the question may be raised whether a wired-in automatization of these procedures is possible and advisable for reasons of simplicity and security. 43H Sketcher, F. L. Bauer, M. Cheru. Basic ideas for the logical design of a computer with independent address operation unit. In the present state of programming techniques, explicit address operations are of an importance equal to that of arithmetical operations. In the sequence control of conventional computers, however, address operations, even if automatized to some extent, are still treated as subordinate. This disadvantage can be eliminated by using a separate address operation unit, including storage facilities. The rigidity of its mode of operations is removed by providing for a spec-ial sequence control. A characteristic is the inclusion of the control counter into the address operation unit. Counted on page 32. Computer People, master file on punch cards. Ed Monosi. For more than a year, Computers and Automation has been maintaining a master file on punch cards containing the names and addresses of all computer people I know. It may interest our readers to kn the procedure we have used. Here are the details. The file was originally assembled in February 1955, from all the lists that we could then find. As of March 1, this file has been used 3 times, for our Who's Who mailing a year ago, for the mailing in August 1955 and announcing the Eastern Joint Computer Conference meeting November 1955 in Boston, and for the mailing in December 1955 announcing the Western Joint Computer Conference in San Francisco 0. February 1956. During March I expect to use it for our second annual Who's Who mailing. Anyone who is interested in computers we believe should have his name and current address in this file. Anyone who sends us his Who's Who entry we put into this file. This file has not been used and will not be used by us or by anyone for advertising purposes, but only for computer people meetings, and for our annual Who's Meo mailing. The file would be available, for example, to the Association for Computing Machinery for AN, announcing their fall meeting, if they should request it. Contents of cards. Each punch card contains 1. Code identifying the source, 4C01. 2. WO initials of the person, 2C01. 3. Last name of the person, 14 columns. 4. Company or organization, 14 columns. 5. Street address, LB columns. 6. City and state, 17 columns. 7. A blank field of 10 columns, free for other uses. The actual location of the information is SHOTVL. In Table 1. Berkeley. In regard to abbreviations, keep on CH. Operators are instructed that any abbreviation that the POST office see and understand is accept. Able when abbreviating names and places. 4. Example, Los Angeles 45 calories occupy easel B columns. But reading it as Los Angeles 45 cal, which omits 2 spaces, abbreviates this phrase in T016 columns, and so it fits into the 17 columns of field 6. In other T-boards, there are 57 ways of being right in this style of abbreviating. The codes identifying sources that have been used so far in field 1 are shown in table 2. Procedure. The procedure that has generally been used. In regard to operations TDTH, these PLL.records is this. 1. Any mailing sent out is marked form 3547 requested, then the undelivered envelopes come back and shot 1T new addresses. Nel VNAMES. And addresses are punched and interpreted. This is the correction file. 2. Any /list of meeting registrants, etc., is punched and interpreted. This is the additions file. 3. The previous file, the correct ions file, and the additions file are sorted RNL. The 5 leading letters of the last name and the first initial, and thus all cards for the same person are brought very close together. 4. The whole file is then edited by a competent clerk. She notices all cards th at are apparently for the same person. She chooses the most recent card lid th a reasonable address, since that is the card most likely to give the best address. She removes the other card s. After several weeks, they are thrmv and a tlay. She also returns cards tvith inadequate address es to the key punch operator to repunch re. Faring again to the source. 5. The cards are then run through a type 407 tabulator to make either slips for insertion in window envelopes or labels for affix. 20. General use. Computers and /automation. The editors of computers and automation propose that this style of punch card be used in general for names and addresses of computer people, so that different contributions int0 the file and out of the file can be made with ease, to the advantage of all concerned. We shall make sure that this master file is never abused, by seeing to it that it is not used for advertising purposes outside of the who's who. In fact, LVE maintain a separate file on metal address plates, which we call RJ3 file, where li put publicly available 1a names of computer people, for mailing 1ist purposes. Here for example li put expiries to computers and automation 1, 2, 3, 4, 5, 6, 7. Top line 1, 2, 3. Second line 1, 2, 3. Columns 1 to 4, 5 to 6, 7 to 20, 21 to 35, 36 to 53, 54 to 70, 71 to 80, 1 to 14, 16 to 18, 55 to 60, 1 to 15, 17 to 34, 36 to 52. Table 1. Layout, JL of card. 1 punches AD column. Meaning. Code identifying sources and classes, as follows. Column 1, last digit of calendar year of source. Columns 2 to 3, serial no of source within year. Column 4, Punch 1 for class computer people. Punch 2 for class management people. Initials of person. Last name of person. Company or organization. Street address. City and state. Blank, not used in master file. 2 interpretation 60 column. Last name. Initials, 1 space. Code identifying source, 2 spaces. Company or organization. Street address. City and state. 21. Know of. Columns. 4. 2. 14. 15. 18. 17. 10. 14. 3. 6. 15. 18. 17. Column 1. Last digit. Of year. Of source. 3. 3. 4. 4. 4. 4. 4. 4. 4. 5. 5. 5. 5. 5. 6. 6. Columns 2 to 3. Serial no. Of source. Within year. 01. 02. 01. 02. 03. 04. 05. 06. 07. 01. 02. 03. 05. 06. 01. 02. Computers and automation. Table 2. Codes identifying sources. COLUFU, 4. Class of. Person. 1. 1. 1. 1. 1. 2. 1. 1. 1. 1. 1. 2. 1. 1. 1. 1. Source. Consolidated list of attendance, Eastern Joint. Computer Conference 1952 and 1953. Western Joint Computer Conference, attendance. February 1953. Association for Computing Machinery, membership. June 1954. Pre-registration, Ann Arbor, June 1954. Wayne University Computation Laboratory, meeting. Registration, June 1954. INST of Management Sciences, membership, April 1954. Western Joint Computer Conference, attendance. Feb. 1954. Computers and Automation Expiries, persons only. About Dec. 1954. Computers and Automation Subscribers, persons only, about December 1954. Joint Computer Conference, attendance, December 8 to 10. 1954. Western Joint Computer Conference, attendance. February 1955. INST of Management Sciences, membership, 1955. Corrections of Who's Who mailing, summer, 1955. Eastern Joint Computer Conference, Boston, Regis. Trajan, November 1955. Western Joint Computer Conference, San Francisco. Registration, February 1956, not yet received. Corrections of WJCC mailing, March 1956. End. 22. Products and services for sale. The computer field. Headings. Following is the preliminary list of headings which we expect to use for products and services in the listing of them in the Computer Directory, 1956, the June 1956 issue. of computers and automation. If you notice headings that you'll wish to be very sure that your products or services are included under, please send us entries at once, see details on P24. Although the closing date for this section was the end of March, we expect to be able to squeeze in additional entries up to April 30th or the first few days in May. Guide to the headings. A. Adding machines. Addressing machines. Analog computers. Analog to digital converters. Arithmetical circuits, FO digital computers. Automatic control equipment. Pound, capacitors, computer types. Card-to-tape converters. Compute components, see also specific types. Computer test equipment. Computers, see also, analog computers. Digital computers, this heading. Computers should be avoided if possible. Computing services. Connectors, computer types. Consulting services. Courses by mail, computer field. Data processing machinery, see also. Digital computers. Data retrieval. Delay lines, computer types. Desk calculators. Differential analyzers, see also analog computers. Digital computers. Digital to analog converters. Diodes, computer types. Electric type A writers, controlled. Electronic tubes, computer types. I. Fire control equipment. I. Keyboards. 1. Line A time printers. Logical circuits, for digital computers. M. Magazines. Magnetic cores, computer types. Magnetic drums. Magnetic heads. Magnetic storage systems. Magnetic tape. Magnetic tape handlers, see also magnetic tape recorders. Magnetic tape recorders, see also magnetic tape handlers. E. Paper tape filing systems. Paper tape punches. Paper tape readers. Patch cords. Photoelectric card readers. Photoelectric decoding readers. Photoelectric tape readers. Photographic recorders, computer types. Plotters. Potentiometers. Printers, see also line A time printers. Electric typewriters, controlled. Publications, see also magazines. Pulse transformers. Punch card machines. E. Recording papers. Rectifiers. Relays, computer types. Resistors. Resolvers. Robots, small. Scanners. Signaling controls. Simulators. Stepping switches. Synchros. Tape-to-card converters. Transistors. Translating equipment. 1. Visual displays. If your products or services do not fit under any of the above headings, we will gladly consider your suggestions for other headings. _and_. 23. Computers and automation. Products and services. A sample entry taken from the 1955 directory from under the heading punch card machines. For sale, is as follows. The computer field, entries. In February we mailed out to about 500 organizations an invitation for entries in Part 2 of the computer directory, 1956, the computer field, products and services for sale. As I prepare the April ISSUE, a great many entries are flowing in. Although the Closing date for this section is the end of March. 11e expect to be able to squeeze in additional entries up to April 30th or the 1st few days in May. In the computer directory, 1955, we published more than 600 entry.s, and lie expect that the number in 1956 will be larger. The preliminary list of the headings that lie expect to use in June 1956 appears on P23. Remington Rand Incorporated, 315 4th Avenue New York 10, NY. /calculating punch. 90-column tabulating card calculating punch, type 332/2/descr, adds, sub, tracks, multiplies, and divides values. Punched into cards, punches results into some card or any or all follow. In cards, various computations can be performed simultaneously /use, in accounting machine procedures $235. Monthly rental, $16,675 sale, prices. Subject to tax. The product description above contains 26 words, there may be up to 50 words but the description, and the whole entry, is subject to editing. End. ** Forum. Association for Computing Machinery. Meeting, August, 1956, Los Angeles. For each entry of a product or service I liefant the following information. The Association for Computing Machinery has accepted an invitation from the University of California at Los Angeles to hold its 11th annual meeting on the Westwood campus. August 27 to 29, 1956. Local arrangements 11th IL. Be under the direction of Dr. Gilbert Kingi. International Telemeter Corporation. CORRE. Spondence concerning arrangements SH0U1DBE. Addressed to the Association for Computing Machinery, Box 3251, Olympic Station, BVER1Y. Hills, California. 1. Name or identification of product, or SIR. Vice underscore 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 on. 2. Brief description, 20 to 51 words, underscore underscore underscore. 3. HOLV is it used, underscore 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 underscore. 4. What is the price range, underscore 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 underscore. 5. Under LVAT headings should it be listed? Organization underscore 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 on. Address underscore 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 under. Filled in by underscore 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 underscore. Title underscore 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 date underscore 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 underscore. Accompanying each entry LOI request a nominal charge of $6 to help defray the cost 0f. Preparing and printing. Contributed papers concerned with HAL 1. Phases of analog and digital computation are solicited. The amount of time to be allotted to each contributed paper will be limited to 15 minutes. Each person wishing to have a paper considered for the contributed program UST submit to the program committee by May 15, 1956, 3 typewritten copies of a 100-10 RDIB extract and 3 typewritten copies of the complete manuscript. The original copy of the manuscript should be on unfolded 8-1/2 by 11-inch 4HITE paper so that it will be suitable as copy for photo reproductions to be provided registrants. At the meeting, the manuscript, including any drawings, must not exceed 4 pages. Send abstracts and manuscripts to J.P. Nash, Chairman, ACM Program Committee, University of Illinois, Urbana, Illinois. Papers for the program LDLL be selected by the program committee after May 15. It will not be possible to consider papers which are not submitted in triplicate or which arrive after the deadline. ENN 24. Off IC Lee. T-Ron ICS 222 explained. Analyzed. Evaluated. All 0 MATIC data processing. /0-IA comprehensive weekly reporting service. This weekly service will provide a single authoritative source of current and detailed information for the individuals in your organization charged with the responsibility of keeping up to date on automatic data processing, by supplying analyses of all available digital data processing equipment, methods for obtaining greater utilization of existing installations, data on basic management policies in the field of office automation, and reports on matters of current importance to all personnel working with electronic computers. IT is designed to inform users of small as well as large digital electronic computers of subscribers will receive 1. Equipment reports, current trends and improvements being made in the field of office automation. The service is organized in such a way that all personnel concerned will be better able to perform their functions, be it at the policy making or operating level. Use of this service will lead to improved utilization of present equipment and offer authoritative analyses and objective opinions on the qualifications of a wide range of automatic data processing equipment. All these materials will be written by the staff of John Diebold and Associates Incorporated, and will naturally reflect the vast experience that this firm has acquired in the area of automatic data processing. See reverse side for further details. Up-to-date and detailed descriptions, analyses and appraisals of available equipment. 2 methods reports, documenting the specific uses of ADP equipment in various industries. Cudahy Publishing Company, 6141 North Cicero Avenue, Chicago 30, Illinois. Date __________________. 3 Policy reports, analyses of important issues of particular interest to management. 4 newsletters, management digests of current interest. Orientation material, explaining the use and operating principles of the equipment to management. 6 special reports and index. Send me your complete brochure and details on automatic data processing service. By John Diebold and Associates Incorporated. Name underscore 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 firm underscore 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 title J address underscore 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 city underscore 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 zone underscore stat underscore e underscore 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 a comprehensive weekly reporting service. MLECDAIA processing gives you equipment reports. Flop service. Current equipment reports containing constantly up to date detailed descriptions, objective analyses and appraisals of available automatic data. Processing equipment. These reports will be objective and will use a common basis of comparison between various pieces of equipment and will adopt standard terminology for the purpose of clarity. A loose leaf binder is provided for convenient filing. These equipment reports will be promptly and continuously revised as equipment modifications are made. This section will provide you with an authoritative catalog of available digital equipment, its characteristics and qualifications. Gives you methods reports flop service. Factual case histories of the applications of ADP equipment in various industries. These will include flowcharts and indicate the specific procedural changes their adoption requires. Pertinent information can be readily located since these reports will be clearly indexed by industry concerned, equipment used and the operations performed. A loose leaf binder will be provided for permanent filing. Gives you policy reports flop service. Critical analyses of crucial management problems concerning utilization of electronic equipment. Example lease vs. purchase, centralization or decentralization, employee recruitment and training, wage and salary surveys, etc. Flop service gives you newsletters, current items of vital interest aimed at keeping management informed on the developments of FICE automation, including notes on professional meetings, operating experience of other businessmen and general data on new equipment. These letters are specifically aimed at management with the purpose of keeping it informed on the ever-increasing utility of either their own or of new automatic data processing installations. These letters will be written in such a fashion that all aspects of the subject can be covered in less than 1 hour's reading per month. Flop service gives you orientation materials, special material to provide the non-specialist with a sound foundation in the field of automatic data processing. This material will also contain a section explaining the use and operating principles of the equipment to both management and technical personnel. Flop service gives you special reports and index. As the need arises, reports on matters of special interest will be published and an index provided to give easy access to the entire mass of material which will appear in automatic data processing service. dash 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 1. John Diebold. Business reply card. First class permit no. 653, SEC 34.9, PL. And R, Chicago, Ill. Cudahy Publishing Company. 6141 North Cicero Avenue, Chicago 30, Ill. And Associates Incorporated. Is a firm of management consultants. With a well-rounded staff which has many years of practical experience in the fields of engineering, mathematics, and business management. John Diebold and Associates have done extensive work in the field of office automation and numbers among its clients. Many well-known organizations using both large and small automatic digital equipment. Published by Cudahy Publishing Company Flop. Service 6141 North Cicero Avenue, Chicago 30. Computers and Automation. Forum. Wayne University, Detroit. Summer Program on Computers. July 23 to August 11, 1956. Arvid Jacobson. Director, Computation Laboratory. Wayne University. Detroit T1, Mitch. Following is a preliminary announcement of our Sunooner program dealing IITH electronic computers and their business and INDUSTRIA1 applications. This will be the fourth summer in Ilhesh these intensive and comprehensive training courses will be offered. Last summer, for instance, nearly 400 students from various parts of the country attended the summer program at Wayne University. Nationally KN0TLN. Specialists participated as lecturers and discussion leaders. We would greatly appreciate it if you I'll make mention of our program in computers and automation. As UKNM, the shortage of trained personnel in the computing RNHENE field is extremely acute. It is important that we train people for this new field which is so intimately related to our INDUSTRIA 1 progress and national security. Wayne University. Computation Laboratory. Sunooner Program. Preliminary Announcement. The Computation Laboratory of Wayne University is again offering an intensive Sunooner training program of 3 T1 courses. Every effort will be made to have as broad a coverage 0F. The important areas in computer development TS as IR achieved in our 3 previous summer programs. Like LC, competent and qualified experts from various parts of the country will constitute the staff as before. First course, July 23 to 28. Automatic computers there. Application and evaluation. Thorough coverage of computer principles and organization, fundamentals of programming and coding. Illustrative examples drawn from engineering and business. Survey and evaluation of available equipment. Lectures, DIS. Science and tutorial sessions. Laboratory. Periods in the solution of problems on Baruch J1S. UDEC. IBM 650, and other equipment. Visits to other local industrial and business computation centers. Second course, July 30 to August 4. Electronic data processing. Induziness and government. Recent developments in the application of electronics to business. Preparation for the introduction of electronic data process in G. Case histories and critical evaluation of major projects underway. Emphasis on approach TVIT. Respect to equipment and different bus INESS systems. Programming and flow CHARTIN G0F. Business applications. Consideration of data. Processing from the standpoint of optimization. In terms of mathematical programming. Lectures, conferences, and laboratory sessions. Computation laboratory equipment available for processing programs prepared by students. Also major data processing systems in the area TLLBE. Available for demonstration and run NING0F. Sample programs. In this course it will be assumed that THE students have taken the first course THAVE. Equivalent training or experience. Third course, August 6th to 11th. Applications of computers to engineering, science, and industry. Study of applications with special attention to numerical methods and advanced programming techniques. Illustrative PROB 1 EMS. Will be taken from Englishneering, Physical, Social, AQD Management Sciences. Net areas of application will be explored and new mathematical and programming methods will be presented. Scheduled lectures in the major areas will be held. Discussions and conferences will be arranged for exchange of experience and net techniques. The Burroughs UDEC and the IBM 650 will be available for student use during laboratory sessions. Large-scale electronic computers will A1S0 be available in the area for demonstration and solution of sample problems. *I. The final program with full information on lectures, staff, and other pertinent information will be distributed well in advance of the summer courses. For further information, if RITE to A.W. Jacobson, Director, Computation Lab, Oratory, Detroit 1, Michigan. And 27. Publications for Business on Automatic Computers, Reference Listing. Part 2. N. Chappie. Illinois INST of Technology. Chico, Ill. This paper supplies a reference listing of TV Learson, Electronic Accounting Machine DA. Publications for Business on Automatic Computers. Developments, IBM, Workshop for Management. This reference listing is in addition to the basic, New York, Management Magazines Incorporated, 1955. Listing and the supplemental listing that were pages 294 to 300. Published in Computers and Automation for SEP TV Learson, The Machine Accountant's Role in September, 1955, and February, 1956, respectively. Electronic Data Processing, Punched Card 1/0 types of publications are cited in his reference listing. The first type is on various aspects of automatic computing equipment and devices, and the publications are listed on DER the following headings: particular automatic automatic computer listing, special purpose equipment, particular devices, paper tape, and punched cards. The second type of publication CITE DIN. This reference listing is on the general application and use of automatic computers in bus in S. This general listing is NOL, further subdivided. Because the publications cited usually conta in. Repetitions and further elaborations of the matter. EL covered by the publications in the basic listing and in the supplemental listing. To facilitate reference, the order of listing within each major grouping of the publication S cited in this reference listing is alphabetic by author. To conserve space, annotation has BECN omitted, and items from NetS magazines have been omitted. ****. Part 2 of this listing appeared in the Mal Ch. 1956 issue of Computers and Automation. Marjorie R. Hislop, A Survey of Machine Systems for Literature Searching, New York, American Soci. Eddy for Metals, 1953, 10 pp. Grandjean G. Jetlet, A Survey of Available Electronic Computers, Journal of Accountancy, Volume 96, Number 2, August 1953, pages 182 to 189. Paul Kircher, Electronic Computers and Accounting. Industrial Logistics Research Report Disc US. SI on paper number 33, Los Angeles, UCLA, 1953. 41 pp. John A. Clay, Are You Getting Ready for Electron? ICS, Banking, Volume 46, Number 5, May 1954, pp. 38 to 39. Benedict Cruz, Electronic Brain keeps tab on 11,000. Rexall Stores, American Business, Volume 24, No. 12, December 1954, pages 12, 41 to 44. John Cord Lagaman, If Robots Run the Works, N.A. Shins Business, Volume 39, Number 3, March 1951. Pages 31 to 33, 80 to 81. C.C. Laubacher, EDA Restricted Survey, Electronic Data Processing in Industry, Net York, American Management Association Incorporated, 1955, pp. 65 to 69. John Lear, Can a Mechanical Brain Replace You? Colliers, Volume L31, April 4, 1953, pages 58. 63 also, in condensed form, Science Digest. Volume 34, Number 2, August 1953, pages 42 to 47. Newell, Volume 3, Detroit, Punched Card Publish. Inco, 1954, pages 7 to 9. Robin Leatherman, Getting Facts Faster, Systems. Volume 17, Number 4, April 1953, pages 7 to 8. Lawrence P. Lessing, The Electronic Era, Fortune. Volume 44, Number 7, July 1951, pages 136. Everett J. Liversey, Electronics in Savings Operations, Banking, Volume 47, Number 10, April 1959. Pages 41, 134. Eve. J. Liversey, The Electron in the Bank. Banking, Volume 46, Number 9, March 1954, pages 74, 76, 78. Warren P. Livingston, Automatic Accounting Mock. Ines, Internal Auditor. Volume 10, Number 4, December 1953, pages 31 to 39. A. T. Mayerson, ETAL, A Machine System for Echoing, Storing, and Searching Engineering Data. On Electronic Components, Columbus 0, Battelle. Memorial Institute, June, 1952, 21 pp. William L. Martin, A Merchandise Control System. Trends in Computers, New York, Institute for Radio Engineers Incorporated, 1954, pages 184 to 191. G. M. McDowell, Applying Electronic Machines TB. An Inventory Problem, Workshop for Mana GE. Ment, New York, Management Magazines Incorporated. 1955, pages 364 to 368. W. W. McDowell, Will Electronic Principles Make Possible a Business Revolution? Trends in Computers, New York, Institute for Radio and Engineers Inc., 1954, pages 9 to 12. Russell B. McNeil, A Look at Future Developments. Electronic Data Processing in Industry, New York, American Management Association Incorporated. 1955, pages 237 to 240. J. W. Millikan, Computers to Control Operations. Railway Age, Volume 138, Number 2, January 10, 1955. Pages 138 to 139. Don G. Mitchell, Information, What We Want, When We Want It, Systems, Volume 19, Number 4, July. August 1955, pages 8 to 9. Don G. Mitchell, Introduction, Electronic Data Processing in Industry, New York, American Management Association Incorporated, 1955, pages 9. 14. Don G. Mitchell, Why We Are Building an Electron IC Data Processing Center, American Business. Volume 25, Number 6, June 1955, pages 34, 36. W. M. J. Morlock. Greatest Electronic Expansion to be in Office Mechanization, The Office, Volume 41, Number 3, March 1955, pages 7 to 10, 12, 15 to 16. Office Methods Division of Navy Department, What About Electronic Computers, Office Executive. Volume 28, Number 2, February 1953, pages 22 to 23. Asher Opler, Save Time, Money, with Computer. 28. Chemical Engineering, Volume 16, Number 10, October 1954, pages 197 to 208. ComJLUTTR's Anti. Carlo Orkilt. Approaching Automation in a Co. Utility Insurance Co. Computers and Automation. Volume 4. Number 2, February 1955. Pages 19 to 22. Automation. Roddy F. Osborne. A First in Industry. Systems. Volume 18. Number 1, January 1954. Pages 9 to 11. Roddy F. Osborne. Begin with a Big Electronic Computer. The Office. Volume 42. Number 1. July 1955. Pages 72-6. 81-85 to 86. 88, 90, 92. Also. In condensed form, Management Review. Volume 44. Number 8, August 1955, pages 559 to 560. Roddy F. Osborne, General Electric installs Electronic Computer for Accounting Operations. Management Methods, Volume 5, Number 3, February 1% 4. Pages 52-53. Joseph Pillay, Electronic Accounting Possibilities. NACA Bulletin Conference Proceedings, Volume 34. Number 11, July 1953, pages 1516 to 1531. Joseph Pillay, Electronic and the Accountant. Progress through Sharing, New York, American. Institute of Internal Auditors, 1954, pp. 11-27. C.R. Pippinger, Information Handling in Business. Operations, Seminar on Operations Re. Search, New York, Railway Systems and Pro. Sedeurs Association, 1954, pages 41-45. Fletcher Pratt, The Human Relations of Computers. And Automation, Computers and Automation. Volume 3, Number 10, December 1954, pages 6-7. Dudley M. Pruitt, Insurance Offices Foresee Many Jobs for Electronics. The Office, Volume 37. Number 1, January 1953, pages 79-81, 193. A. E. Puccio, Automation is in the Cards, Prepare for it, NACA Bulletin, Volume 35. Seconds. Shanghai, Number 10, June 1954, pages 1245-1251. Jan A. Rajkman, Digital Computers, Instruments. Volume 26, Number 11, November 1953, pages 1711, 1739. 1740. A. H. Raskin, Automation Puts Industry on Eve of Fantastic Robot Era, Computers and Automation. Volume 4, Number 5, May 1955, pages 27-28. 38. William A. Reardon, Use of Punched Card Account. Ing. Accountant IS Digest, Volume 20. Number 1. September 1954, pages 37-38. Mina Rees, Applying Computers to Machine Control. Machine Design, Volume 25, Number 10, October 1953. Pages 324-334. Arvid E. Roach, Life Was Too Short. Steel, Volume 131, Number 21, November 29, 1952. Pages 129. WMF Rowe, Electronic Billing for Utilities. Systems, Volume 19. Number 1, January-Feb 1955. Pages 20-21. A.B. Sands, Electronics Chart Sales Picture. Systems, VL18, Number 8, November, December 1954, pp. 6-7. David Sarnoff, Electronics in the Office, Office Management and Equipment, Volume 13, Number 8, August 1952, pp 20-22, 70-77. C. W. Schmidt and R. Bozak, Production Scheduling and Labor Budgeting Th Computers at Lockhead, Georgia, Electronic Data Processing in Indus. LLY. Net. York, American Management Association. Inc., 1955, pages 206-213. A. J. Schnees, Electronic Processors in the INSER. ANS Industry, The Office, Volume 41, Number 1, Jan. 1955, pages 112, 196-197. Hans Schroeder, Computers to Make Administrative Decision. Computers and Automation, Volume 4. Number 3, March 1955, pages 28, 29. Julius Shiskin, An Application of Electronic Computers to Economic Time Series Analyses, Anal. YSTS Journal. Volume 11, Number 2, May 1955, pp. 35-37. 29. Julius Shiskin, Sentinel Compunction on Univnk. American Statistician, Volume 9, Number 1, February LL. Pages 19 to 23. Ralph G. Sin, Simplify Your Routines to Prepare. For Electronics, The Office, Volume 41. Number 1. January 1955. pp 114. Robert M. Smee Th, Automation in the Office, Office Management, Volume 16, Number 3, March 1955, pages 28. 29. John A. Sunnickson, Streamlining Operations. Of FICE Management Series Number 131, New York, Amer. Icon Management Association. Inc., 1952, pp. 14 to 21. Gordon Spencer, Statistics and Automatic Computers. Computers and Automation, Volume 4, Number 1, Jan. 1955, pages 6 to 7, 13. Award Steele, Automation How Soon and How Much. Audi T. Graham, Volume 31, Number 3, March 1954. pp 42. 47. Alan H. Stillman, Punched Card Control for Automatic Machines. Product T. Engineering, Volume 26. Number 6, June 1955, pp 172 to 176. Mill Tunstone, Data Processing Begins at 20 Me. Automation, Volume 2, Number 8, August 1955, p. 48. Leonard W. Swanson, Tools of Operations Research. Operations Research Seminar, Chicago, Society for the Advancement of Management, 1954, 8 pp. B. W. Thomas, High-Speed Computers, ISA Journal. Volume 2, Number 3, March 1955. pp 73 to 76. K. D. Tozer, Application of Automatic Computing. Machines to Statistics, Automatic Digita 1. Computation, London, Lierne Gestes Stationery. Office, 1954, pp 166 to 178. George F. Trexler, Public Utility Customer Account. Ing on the Type 650 Magnetic Drum Data Processing Machine, Journal of the Associo-0N. For Computing Machinery, Volume 1, Number 4, DCT. 1954, pp 172 to 176. John H. Stroll, HOH Smart Are Thinking Machines. Atlantic Monthly, Volume 194, Number 1, July 1954. pp 62 to 65. Also, Science Digest, Volume 36. No. 4, October 1954, pp 15 to 19. A. C. Vancelo, Programming the UNIVAC for Clear. Eichel Production, Systems, Volume 19, Number 3, May. June 1955, pp 15 to 16. George II. Wadsworth, Approaching Mechanical AP. Applications Wisely, NACA Bulletin. Volume 36. Number 8, April 1955, pp 1069 to 1077. Edward T. Wagron, Electronic Computers, No Easy Answer, Office Management and Equipment, Volume 15, Number 3, March 1954, pp 32 to 33, 76. 78 I Volume 15, Number 4, April 1954, pp 24 to 25. J. S. Warshauer, How Does Accounting Stand with Electronics? NACA Bulletin, Volume 34, Number 8. April 1953, pp 965 to 972. Thomas J. Watson, J.R. The Revolution in the of FICE, Journal of Machine Accounting SYSTEMS. And Management, Volume 6, Number 2, February 1955, pp. 5-6, 17. Oliver Wheely TBY, Automatic Handling of Bus in ESS. Data. Trends in Computers, New York, Institute. For Radio Engineers Incorporated 1954, pp 75-79. John S. White, How We Planned for Use of EIEC. Tronic Equipment. NACA Bulletin, Volume 36. No. 10, June 1955. pp 1343-1347. K. B. Willett, Electronics Will Increase Demand. For Office Workers. The Office, Volume 37, No. 1, January 1953, pp 96. R. T. Wiseman. Combined Operations in a Life in Surensko, Computers and Automation, Volume 2. Number 9, December 1953, pp 11-13. End. Computers and Automation. Forum. Removable and interchangeable. Typewriter type. A. C. Hancock. Remington Rand, Nell Y. York, N.Y. Removable and interchangeable typewriter. Type a Nell Y development permitting the typist herself to change one or all of the characters on her machine in a matter of minutes appears on the Nell 1956 model Remington standard type. 11 writer. The type writer, in addition, has an expand ed keyboard with 44 characters, which enables the user to take greater advantage of the NE1V. Interchangeable type, in its standard arrange meant it provides the 4 extra characters: section mark, paragraph mark, plus sign, and equal sign. All current and old model Remington stand ARDs and electrics can easily be re-EQUIPPED. LVITH special type bars to receive the Nell V inter. Changeable typefaces. The Nell Y interchangeable type allows one machine to do the iFork of SEV. Errol, and makes ordinary office type 11 RITERS much more versatile. In making type changes, the typist does not have to touch the type with her fingers, nor remove typing from the machine. A simple pair of TLL teasers, she removes the old type block, selects a new one, and snaps it into place. The clue to the device is a tiny spring retainer clip on each type block for HICH. Snaps onto the type bar. Once in place, the character is as firmly fixed and perfectly aligned as ordinary type. Government, business, or professional of FICEs whose TLORC require the use of Spec IA1 type characters mathematical, medical, engineering or musical SEM calls, for instance, can now keep a supply of these characters on hand and snap them into their machines as need. Instead of investing in special machines or entering them by hand into typal T10 text. Foreign language characters, symbols, and punctuation marks idle also be available. Tommy et. Typing needs of foreign legations and organizations, import-export concerns, and ege. Foreign language departments. Note by the editor, wherever an E1 ECT RIC type return is used as an output by an automatic computer, this development has an IMADAM D8 and important application. The Computer Directory, 1956. Notice. The June 1956 ISSUE of Computers and Automation will be the second issue of the Computer Directory. Last year I published the FRT issue, 164 pages. Our present plans for the June 1956 directory follow. Part 1 of the directory in 1956 will be a cumulative roster of organizations in the computer field based on the last cumulative ROS. TER, published December 1955, containing about 330 entries, and brought up to date. Entries in this roster will be free. If you know 0f, any changes, additions, or corrections T1J-C11 should be made in the entries, please tell us. Part 2 of the directory will be the second edition of the computing machinery ID. Products and services for sale. 0VER-600. Entries on 21 pages appeared in the first edition in June 1955, a considerable increase is anticipated. The previous entries, and blank forms, were sent in February, to suppliers for Rev 1L, checking, and additions. A nominal charge of $6.00 an entry is requested from each supplier in order to help defray the cost T0F. Preparing and printing the directory, but if the charge is not paid, the entry may still appear in condensed form, if desirable to make the listing complete. Part 3 of the directory will be the third edition of the Who's Who in the computer field. In the June 1955 issue, about 7,500 entries appeared on 96 pages, of these about 2,600 TVR full entries, and the remainder REF entries. Our present plans are to publish only NELF or revised Who's Who Informity 0N in the June 1956 directory. Blank forms or NEL / or revised entries were sent in March to all computer people we know of. A nominal charge of $2 an entry or other support of the Who's Who was requested from each perso.n whose entry is printed, in order to help defray the cost of preparing and printing the Who's Who. The main reason for the nominal charges mentioned above is that we look on the directory as a service to many people in the C0M computer field, yet so far it has not paid for itself, and we need to make a compromise, publishing at least some Informity 0N of 0UT. Everything that should appear in the directory, but fuller information for those TVH0HAVE shared directly in the cost. 30. Conted from page 19, computers and by LOONs of a block diagram. Uncertain obvious possibilities and advantages of use are discussed, e.g. free use of several index registers, very simple execution of Enderungen 2. Art with co-n sequences to the assembling of subroutines, PR0. Granunning, to a 1 extent, free of address SES. ID without use of compling routines. 44 A. Schluter, Gottenju. Considerations on a high-speed parallel computer. Using of ferrite toroids in high-speed compute. ERS all 011s. The construction of a large-scale rapid access memory and the installation of machine or DERs consisting of a great number of elementary machine operations. It is examined to which degree these possibilities may be used to facilitate combination of complicated routines. THEAUTH0R discusses the introduction of a great MERN BROF index or step registers. 64 are provided and of special orders for automatic connection of library subroutines and for simplification of counting. 45 CS Scholten, Amsterdam, Nederland. Transfer facilities between memories of DIF. Different types. The problem dealt with here arises from the use of really large-scale memories. Select ing. Information directly out of these memories requires a lot of apparatus and a waste of memory space on account of the long addresses that must be used. Suggestions are made how to avoid these difficulty. IES and AMST other methods, the use of buffers is found to be very convenient. Other advantages of buffers are discussed, and finally a few words are said about what has been done in the RMAC, Automatisch Reken Mas GNE. Mathematisch Central regard to the community cation between its drum memory and its magnet IC core memory, part of which serves as a buffer for orders. 46W Shut, Darmstadt. Technical specialties of DERA. 1. Stabilization of flip-flops and inverters. Stabilization is achieved by clamping diodes. By this, signals are to a high degree independent from operation voltages and values of components. Attenuated signals are reamplified to rated, nominal, amplitude. 2. Pulse timing unit. Timing pulse gear wheel fixed to the rotor of the magnetic drum serves for control of electronic devices producing timing pulses. This unit consists of an aluminium disc, the nickel P18D, circumference of which has milled slots for remaining. A 5-track high-precision circular scale. Record ing by special magnetic heads. Advantages: high robustness, timing tracks cannot be iveshed out. Also in case of great distance head layer high peak voltages and optimal pulsing forms. 3. Selection of reading heads. Reading heads are selected by electronic selection switching devices consisting mainly of germanium diodes. By this circuit high bandwidth and crosstalk transmission equivalent can be obtained. 4. Data transfer between punched card input, output unit and computer. Because of different modes of number rep RE. 32. 4. Automation D. Sentation in the punched card unit, parallel, and in the computer, serial, a code modification muse.t. be carried out when transferring data. Locations of cells of the same value are recorded together. In groups, the value itself is once recorded separately to or from the magnetic drum. Synchron. US operation between punched card unit and magnetic drum is not necessary. 47. Speaker, Z-Schweiz. Control panel and input and output facilities of Vermouth. Input and output of information for ERMET here. Carried out WITH punched card apparatus 0F the Remington RAN type. Mechanical crossbar select. Or serve for buffer storage and for selection purposes. Results are recorded with a typewriter, the printing arrangement of which may be selected. On a plug board, in addition there is a tabulator of our own development which prints 216 digit numbers per second. For manual input of ORD-ERS and numbers, several keyboards with Mesihan iCal interlocking are provided. Visual indication of numbers is performed with digit carrying wheels. Driven by an electric motor, these wheels display a 16-digit number within 1/2 second. The discrete apparatus are illustrated by slides. 48 F. Stalls, Sindelfinju. Experiences with tubes and other components used in electronic digital computers. Man. Manufactured in Germany. Technical literature of the USA presents many reports on usability and reliability of electronic components for computers. Up to now in Germany it had not been possible to make similar experiences on a large number of components. Since spring 1954. The IBM at Sindelfingen near Stuttgart is manufacturing the electronic calculating punch Type 604 equipped with German components. BE-SID CSA short technical explanati 0N of IBM Type 604. The author gives a descriptee 0N of used methods for testing, control, and statistical evaluation of all components. This control has now been extended to some 10,000 tubes and so me 100,000 resistors and capacitors. It is how n to which degree the different components contribute to the total number of errors. Further, the kinds of errors in different components are expressed as percentage. Most of the tested components like were defective have been eliminated at preventive maintenance in order to avoid a failure of the machine during computing. The method of preventive maintenance is described because an especially high reliability of computers is reached. The results obtained in Germany are compared with those obtained in USA. 49 Thun, Hoff. Physical programming tables are described which make possible the determination of 3 address instructions by means of physico-technical considerations without difficult mathematical transformations. This method of programming may be useful for digital and analog computers. 50B Thuring, Karlsruhe. Computers and the automatic programming of UNIVAC by the A2 compiler system. The A2 compiler system provides a means 0F automatic conversion of a defined instruction code into another defined instruction code, the latter of which is the own code of the UNIVAC, the so-called CLO code. The programs directing the computing operations are encoded by the CLO code, which is a address code determining the key of the elementary operation steps. However, as the problems to be computed are originally given in a specific mathematical form requiring event ULI complex instructions, as for instance for calcu 1 a logarithm, a sinus, a polynomial sum 0r, for transferring a certain quantity of number s, etc., these complex instructions initially have to be encoded by a so-called pseudocode. In many cases these instructions TDLLB 3 address instructions, the addresses of which may often be VARI able. The conversion of the pseudocode into the CIO code is accomplished automatically in the UNIVAC by a compiling method. Using this method 0D. Several CLO subroutines have to be stored 0NA. Magnetic tap E, library tape. Another tap E, pseudocode tape, contains the problem converted by the pseudo-code. On the compiler instruct on tape the proper compiler program is written, by which the required subroutines are selected by means of the pseudocode instructions. The compilation of these tapes will give the final CIO instruction tape. The contents of this tape is transferred into the working storage and will be used for performing the computations. The essential peculiarities of the CLO code E and the pseudocode will be explained by samples. 51 Ube, Wetzler. Expanded switching technique at Z5 according to experiences. The author reports on some special modifications of teaching technique applied to, or being prepared for, Z541, further simplificati 0n. Of programming, 2, facilitation of check engine. Case of occurrence of an error, 3, reducti 0n 0f. Time necessary to solve a problem. 1. Jump order, conditional or not conditional, which causes automatic punching of certain words to be scanned, automatic programming. In case of similar problems. 2. Constant storage, constants of form 2. A. B. Manually adjustable enables easy checking of the arithmetic unit. Recording of contents of punched tape by automatic type. Writing. 3. Operations to be chalked out, sin y1x. Maximum integral multiple of x. 52 H. Unger, Darmstadt, Hanover. Works carried out by the Darmstadt Mathematical Computer Group. 1. Works on programming, position, expansion and examination of the instruction list. 33. Automation. Punched cards for input and output scrutinies. Time waste with and without address and reach n. Work invention of Funversprung, J-umping in spaces of 5 words, effectiveness and size of a. Rapid access memory for storing instructions and numbers. Special conversion routines and sub routines, computing with double accuracy, compute. TDTH complex numbers, computing of elementary functions. Program input and insertion of sub routines, SUI table methods and time necessary for making programs. 2. Problems carried out, numerical methods. Works on the Darmstadt Bull punched card unit. Works on other punched card machines T.DTHE1EC. Tronic arithmetic unit and on the Swedish C0M. Puter BESK. Statements on different methods 0f. Practical analysis. 53 S. Vajda, Teddington/England. Experiences in linear programming on computers. Remarkable progress has already been made in the technique of processing and exhibiting data by means of electronic equipment. However, it is equally important to develop methods of computation enabling us to draw conclusions. Linear programming is one of these methods. It deals T.DTH the maximization of a linear form, having variables subject to linear inequalities. The solution of such a problem may also require the use of electronic equipment. The talk contains an account of some experiments in linear programming on computers. Various methods will be mentioned and a new method will be described which may have some advantages over the methods used hitherto. 54 R. de Vogelaere, Notre Dame, Indiana/USA. On a net.v method to solve in the large S0ME. Nonlinear differential equations use in G. High-speed digital computers. The method depends on work of Poincare and Birkhoff. It is based on properties of Tran S4 machines T such that there exists an involution R. WITH, 1 R, 2 equals 1. It can be applied, among others, to D if R. Engel equations of type X::::, F, xt, LDTHF, xt, F, xt plus T. And with a symmetry condition, such as F, xt, F, xt. Or of type X equals U, xy, y equals dot. U, xy, with xo. U, au, x, y. The transformation T is deducted frm the di. Differential equation, the relations r equals 1, tr. 1 depend on the symmetry condition. The method permits to obtain most 0f the periodic solutions stable and unstable, by INTE. Grading with initial conditions depending on 1 parameter. The integration can be performed .dth. Any step-by-step method, for instance the authors, computers and 1. J of Research, NAT Bureau of STA 2 DARDS. March 1955. It has been used for the Stormer S-Pergblom as well as for Duffing S equation XX plus X equals F cos -T. 55K Wank, Ludwigshafen. Experiences and problems for inversion of matrices by punched card methods. Statements on used computers, 0 per ATION. Processing using elimination method time to be spent, experiences and problems on propagation of round-off errors. Matrices up to order 22 HAVE. Been practically treated till now. 56A Van Wijngen Arden, Amsterdam, Nederland. Scientific computing in the Netherlands. The author surveys some special problems solved by automatic computing during the last years. 57 M.V. Wilkes, Cambridge/England. The attainment of an optimum interval of IN. Integration in numeri.cal, quadrature, and solution of differential equations. The procedure performing a numerical integration falls into two parts: 1. The division of the total interval of integration into a number of sub-intervals, and 2. The application of a suitable integration formula to each subinterval in turn. If the subintervals chosen are too large in relation to the formula used and to the AC cur ACY required, truncation errors will be introduced. If they are too small, excessive time will be C0n summed in performing the integration. The PAP-ER is concerned the problem of Davies-Ing methods. Suitable for use with a digital computer, TVHICH. Enable an approximately optimum division into sub-intervals to be made automatically. 58 F. Wipperman, Frankfurt. Use of computers for numerical weather PRE. Diction. A survey is given on the development of methods of numerical weather prediction during the post-war years. Mathematical problems and methods for their solution are discussed. Requirements for computers regarding computing speed and capacity of memory are explained. The achievements of methods for numerical weather prediction are proved by recent results in USA and Sweden. The SE numerical methods are already used for R0 UTINE feather prediction. 59 H. Zemanek, Wien/Österreich. Working on electronic computers and information processing apparatus at the Institute für Niederfrequenztechnik der Technischen Hochschule in Wien. In connection with the working schedule of the Institute on pulsing techniques, firstly problems raised regarding dimensioning of counting registers and then the development of a pulse counting device. Later on TVE began the construction of a computer, the fixed program of which is base 0n. The Galton board principle, for this per P0 SE. Polycathode glow discharge counting tubes WR. Developed, but because of their instability the computer could not be completed. 34. Automation. The next model was an analog computer for solution of equations. Up to the sixth order equipped WITH a STEPSLVTCH device for modification of variables. By this solutions may be found automata Kali to a certain degree. For education P_ERPAS is a simple model 0FA. Relay computer was constructed T-forking with 16 memory cells for 18 binary digits and contract all D by punched tape. In spite of a minimum of TECH nickel consumption, the machine SHOLIS all via TURS of a program sequence controlled computer. Then we have built another relay computer for evaluation of logistic functions. Programming is carried out by means of plug-in cables and adjustment of variables either manually or automatically, by running all possible combinations to find truth value 0 or 1 of the function. A larger program sequence controlled computer shall be developed according to the moderate means at our disposal, using to a high degree transist or as a magnetic drum memory for 180,000 bits is under construction. Moreover, TEV have copied the turtles of Gray Walter using relays and a vocoder, recording only the spectrum of spoken language and thus reducing the band T width to approximately 1/10. FUR. There a computer is under construction automatically producing music-like sequences of sounds and thus having something like fantasy. 60H Zamanek, Wien/Österreich. The logistic relay computer of the Institut für Niederfrequenztechniken. Hochschule Wien. This computer is a further development of the apparatus built by Ferranti in England. It is distinguished by more compact assembly, technical construction, without rectifiers, and some auxiliary ankle safety devices. It has been completed as Diplôme BTLV within the training schedule of our Institute of Technology. In case of a logistic function, it may be fiercely asked for its value E. For this purpose the function can be programmed at the machine by means of plug-in cables, variables can be adjusted, the computer indicates truth value. Secondly, it may be asked th values NMSTB assumed by the variables th at the function assumes a definite value, 0 or 1. Therefore the computer automatically NMST run all possible combinations and indicate those corresponding with the conditions. An example has been carried out, 7 variables give 128 combinations. The running timmy for th is about 2 minutes without stop timmy. A secondary condition, it may be required that only solutions with the truth value 1 shall be indicated. Thirdly, it may be asked in which way a given logistic function may be realized with a minimum of technical consumption. Up to now, no computing machine is known which can solve this Pro B1EM. However, a smaller computer of Shannon and Moore allows discovery and location of superfluous contexts. Computers and list of chairman: Bader, Wilhelm, Professor Dr. Ing, Stuttgart, Ma.R. Kellstrasse 20 Institut für Theorie der Elektrotechnik, Technische Hochschule Stuttgart, Breitscheidstrasse 3. Biermann, Ludwig, Professor Dr. Phil. Max Planck Institut für Physik, Göttingen, Bottinga R. Strasse 4. Billy L. Heinz, Dr. Leiter der Arbeitsgruppe. Nummeriechen im Institut für Instrumentenkund in der Max Planck Gesellschaft, Göttingen, Bunsenstrasse 10. Gundlach, Friedrich Wilhelm, Professor Dr. Ing. Lehrstuhl und Institut für Hohe Frequenztechnik, Technische Universität, Berlin Charlotte. Enberg 2, Jabenstrasse 1. Heinhold, Joseph, Professor Dr. Munchen Soln, IRM. Gardstrasse 15 Lehrstuhl // NDTE. Mathematik und Mathematische Statistik, Tech. Nisk Hochschulen Dülnchen. Kamk, Eric, Professor Dr. Phil, Tübingen, Frisch. Linstrasse 27 Mathematisches Institut der Universität Tübingen. Kupfmuller, Karl, Professor DRLNGEH, Darmstadt. Oli Strasse 40 Director des Instituts für Allgemeine Fernmeldetechnik, Technisch Hoch. Schule Darmstadt. Sauer, Robert, Professor Dr. Mathematisches Institut der Technischen Hochschule MNC Hen. Munchen 2, Walter von Dyck Platz 1. Walther, Auden, Professor Dr. Director des Instituts für Praktische Mathematik, IPM, TECH. Nisk Hochschule Darmstadt. Willers, Friedrich Adolf, Professor Dr. Rayer. Nat.H.C. Dr. Phil, Dresden A36. Kostschetterstrasse. 6 Institut FLLR Angewandte Mathematik. Technische Hochschule Dresden. List of speakers. Adam, Adolf, LNG, Dr. Phi 1. Konsulent für Mathematik und Statistik in Wirtschaft und die Zwickverskung, Österreichische S, Ixtof. Werke AG. ABT. UAW, Linz, Donau, Österreich. Aachen, Howard H., Professor DRLNGEH. Dr. Director de Computation Laboratory of Harvard University, Cambridge 38, Massachusetts/USA. Bachmann, Karl-Heinz, DIPL Math, Dresden N23. Wildermannstrasse 42 Bielinstitut für Angewandte Mathematik, Technische Hochschule 1e. Dresden 1 / Bauer, Friedrich Ludwig, Privatdozent, Dr. MUN. Chen 42, Porzschacherstrasse 40 Mathemat. Isches der Technischen Hochschule. Munchen. BELEVLTCH, Vitold, Dr. 97, Rue Gabriel, Brus. Cell/Belgieninstitut pour one encouragement. De la Richie le scientifique dans l'industrie. Et1T Eric Ultieur, IRSIA. Biermann, Ludwig, Professor Dr. Max Planck Institut. Tut Fr Physik, Göttingen, Böttingerstrasse 4. Billing, Heinz, Dr. Leiter der Arbeitsgruppe. Numerisch Maschinen im Institut F11R. Instrumentenkund in der Max-Planck-Gesellschaft, Göttingen, Bnsenstrasse 10. Booth, Andrew D., D.Sc. Director de Birkbeck. College Computational Laboratory, University of London, 21, Torrington Square, London W. CL/England. 35. Automation. Baten-Brusii, Hermann, Dip 1 Math, Darmstadt T. Alexanderstr. 33 Institut für Praktische HE. Mathematik, Technische Hochschule Darmstadt. Brocade, Klaus, Sindelfingen, Bo Bellinger Ali. IBM Deutschland. Comet, Stig. Laborator Vorstand von Mathematik. Masken den Arbeitsgruppe, Drottningaten 95a. Stockholm 6/Schweden. Dijkstra, Etzger W. Mathematisch Centrum, 2c. Bauerhavister. 49, Amsterdam/Nederland. Dreer, Hans Joachim, Dr. Darmstadt, Bess. Unger Str 38 Institut für Praktische Math. Ematik, Technische Hochschule Darmstadt. Eckert, 0, Dip 1 Physics. Zentralaboratorium. Stiati T Magnus IAAG, Lauf, Pegnatese, AM Steg 14. Froe, Theodore, Weil am Rhein, Hauptstrasse 181. Gillard, Hans, Dipling, Darmstadtschuknecht. Strasse 48 Institut für Praktische Mathematik, Technische Hochschule, Darmstadt. Goli 15 Tine, Hermann H., Professor Dr. The Institute for Advanced Study, Electronic Computer PR0. Jecht, Princeton, NJ/USA. Green, George B. President, Marchant Research Corp., 1475, Powell Street, Oakland 8, California/USA. Hansen, Walter, Aberregierungsrat, Dr., 24b, Has. Lohen-Holstein Deutsches Hydrographisches Institut Hamburg. Harold, Kurt, Dr. Zentralversuchsstelle Fr. HF Forschung, Nürnberg, Lehrstre. 56. Hoffman, W., Dr. Arbeitsgruppe Nummer CHE. Rechenmaschinen im Institut für Instrumenten. Kund in der Max-Planck-Gesellschaft Gott. Bunsenstrasse 10. Householder, Alston Scott, Dr. Director, Math. Ematics Panel, Oak Ridge National Laboratory. Oak Ridge, Tennessee/USA. Klein, Paul E., Dr. Ing. Fellbach bei Stuttgart. Oberlandstre. 23a. Kohler, Helmut, Dipl Math, Stuttgart, AutoIt Sky. Strasse 7-9 IBM Deutschland. Lederle, Trudpert, Dr., Heidelberg, Grabenstrasse. 14 Astronomisches Recheninstitut Leoalberg. Lehmann, N. Joachim, Professor Dr., Dresden A21, VO. Glerstrasse 25 Institut für NGETFNTE. Mathematik, Technische Hochschule Dresden. Lilac, Hans Otto, Dipling, München 23, Och. Ennerstrasse 7 5 Institut FLLR Elektrisk. Nachrichtentechnik und Messtechnik, Technisk. Hochschule München. Leser, Gottfried, Diping, München 13, Shell. Ingstrasse 75 Institut FLLR Elektrisk. Nachrichtentechnik und Messtechnik, TECH. Nisk Hochschule München. Linsmann, Marcel, Dr. Math. Chef de Travaux. L'Université de Liège, Ludic/Belgienne. Lupstra, Bram J. Mathematisch Centrum, 2 Sibo. Havester. 49, Amsterdam/Nederland. Muller, W.H., Math. Dr., Nieuwendig 33, Amster. Dam C/Nederland NV Con. Ned. Village. Tigenfabrik Fokker. Allman, Herman, Dipl Physical, G6 Tringen, Rassen. Bergerdiag 46 Arbeitsgruppe NU3 is CHE. Rechenmaschinen im Institut für Instrumenten. Kund in der Max-Planck-Gesellschaft, G3 N, Bunsenstrasse 10. PLLOTY, Hans, Professor Dr. Ing. Director de in. Instituts für Elektrische Nachrichtentechnik. Und Messtechnik, Technische Hochschule 11 U1E. München, München 2, Walter von Dyck Platz 1. Pisola, Karl, Dr. Rare.net. Max Planck Institute. Computers and Automation. Für Physik, Göttingen, Bottinger Strasse 4. Poel, Willem Louis van der, Jr., Schneidstraat Il. Den Haag/Nederland Dr. Neyer Laboratorium. PTT, St. Paulusstraat 4, Leidschendam/Neder. Land. Pouliart, William, Ingenieur Directeur General. De la Division Électronique de la Belle Télé. Phone MFG. Co. 4, Rubedatolage NS, Antwerpen / Belgian. Proebster, Walter, Dipling, GRNNTLALD bei München. Südelfeldstrasse 1 Institut für Elektrisk. Nachrichtentechnik und Messtechnik, Technisk. Hochschule München. Ross, Clarence, Dr. Chief, System DYN AMI CS. Branch, Aeronautic Al Research Lab 0 Rat 0 Re. Directorate of Research, 1204 Irving Avenue UE. Dayton 9, Ohio/USA. Rudischhauser, Heinz, Professor Oro, Rodhistrasse 105. Z Rich 48/SCHT Vase e Genosisk Technisk. Hochschule Zurich. Samuelson, Klaus, Dr., München 13, Il Tensperger. Strasse 19 Mathematisches Institut der Technischen Hochschule München. Sketcher, H. Dr., München 25, Researchstrasse. 19 Mathematisches Institut der Technisken. Hochschule München. SCHLIHER, Alf, Dr. Max Planck Institut F2R. Physik, Göttingen, Böttingerstrasse 4. Scholten, Karel S. Mathematisch Centrum, 2C. Bauerhavestraat 49, Amsterdam/Nederland. SCHLTTE, /L Alter, Dipl. Physical, Darmstadt, Liebe. Frauenstrasse 29 Institut für Praktik. Mathematik, Technische Hochschule Darmstadt. Spießer, Ambrose, Dr. Ing, Rotbuchstrasse 42, Zur. Ich 37/SCH1 Leis Institut für Angewandte LNTE. Mathematik, Genossische Technische Hochschule. Schule Zurich. Stahls, Fritz IBM Deutschland Sindelfingen Bay. Stuttgart. T. Rudolf, Baratender Ingenieur, Vol, H0F. Sala, Worthstrasse 10/1. THURIL: Bruno, Professor Dr., Karlsruhe R1 ACH. Marstallstrasse 22 Forschungsbüro F2R. Theoretische Astronomie und Angewandte Math. Ematik. Uhl, Wolfgang, DIPL Math, Gießen, Eichgarten. Ali 62 Technische Hochschule Hannover. Vajda, Stefan, Dr. Phil, 129, Great Tattenhams. ISPOM/England Admiralty Research Labra. Tori. Vogelaira, Renata, Professor Dr., 63, Rue du Fram. Boitier, Brussels/Belgienne Université Y0F. Notre Dame, Indiana/USA Office of Naval Research. Wenck, Klaus, DIPL Math. Badisk Annalen und Sodafabrik AG, Ludwigshafen. Wigeng Arden, Adrian van, Professor Dr. K.R. Math. Matisch Centrum, 2C Bauerhavestraat 49, AM. Amsterdam/Nederland. Wilkes, Maurice V., Dr. Directeur, the University City Mathematical Laboratory, Corn Exchange. Street, Cambridge/England. Wipperman, Friedrich, Dr., DIPL Med, Frankfurt. Am Main, Domplatz 8 Deutsche Wetterddienst. Zentralstelle, Frankfurt am Main. Zemanek, Heinz, DIPLing, Dr. Techn, Erdberg. Strasse 74 9ths, Wien 3/0 Sturreich ins TITUT. Verniederfrequenztechnik der Technische Hen. Hochschule Wien. End. 36. Applications. Specialists. Technical. Writers. Training. Specialists. with experience in computer programming and operation, punched card systems, and procedures. Here's an opportunity to join the fastest growing organization in the electronic data processing field. Electrodata Corporation, now the third largest producer of digital computer systems, needs personnel who have a thorough understanding of the use of machines in data processing, and who have a desire to advance in the applications and computer field. Experience in the fields of insurance, public utilities, production control, and inventory control is especially desirable. Positions are open in all regional offices and in Pasadena. In complete confidence, write to Milton M. Stone, Manager, Business Applications, Electrodata Corporation, 460 Sierra Madre Villa, Pasadena, California. Forum. Footnote no, trailer note. Bildange, Munich, Germany. 8. AUTOTLE-TIC. Computers. Physicist or engineer. Analog computer. We're looking for an individualist. We'd like him to be of a high order of analytical ability, and to have already become proficient in computer programming in support of activities in the fields of reactor physics, heat transfer, hydraulics, and mechanics. After that he will take the reins, and using his administrative abilities, show us that this is one position that is definitely fitted to the man. If you have the vision to keep on looking ahead and are realistic enough to keep a staff looking ahead right up there with you, then we invite you to write in confidence to General Electric. For now, more than ever, people like you are creating the positions they will continue to grow with. Personal interviews will be arranged with all selected candidates. LB. In writing, please include your experience, age, academy background, and Tech NICA references. Mr. E.P. Galbraith, Technical Personnel Placement. General E. Electric. Richland, Washington. 37. Content from page 11, Computers. Variety of problems encountered in government operations. It must be highly flexible in character. Moreover, the facility will provide our staff with increased research and engineering experience. Modular construction of electronic equipment. Project Tinkertoy. There is one other important example off fork, along quite different lines. This deals with our work for the Navy Bureau of Aeronautics on a system for the mechanized production of electronic equipment. The extensive dependence of modern military equipment upon electronic devices led the Navy to seek ways of increasing its mobilize at ion potential with a system which might eliminate some of the previously experienced difficulty. IES. Important among these difficulties are such factors as 1. Extreme dependence on many sources of supply for components which during periods of rapid expansion of production can lead to many bottlenecks. 2. Long lead time necessary to get large-scale production lines for military equipment into operation. 3. High degree of variability in product performance characteristics, leading to extensive and complicated maintenance problems, particularly for military equipment. Various estimates give the maintenance costs of military electronic meant as 5 to 100 times the initial cost, and 4. Extensive dependence of production techniques on hand methods. It is a curious anomaly that this industry, whose products have been widely heralded as making possible automatic factories for other industries, is in its OLVN production technique extensively dependent on manual labor. Basic design systems for the production of electronic equipment they've changed very little since the mid-1920s, LIHE the inverted cake pan type of chassis SMB1Y. EVOLVED. The project consisted of TTLO parts. First, the development of a modular system for the design of electronic equipment, and SEC0ND. The design of automatic machines for processing and assembling the components of the modular system. Solution of the first was considered essential to the successful completion of the second, since early analysis led to the conclusion that any mechanized system which W0U1D assemble conventional components in conventional layouts would be unacceptably cumbrous 0ME and inflexible. The modular design system is based on a standard building block, a 7/8 square, notched ceramic wafer. Components such as resistors, capacitors, repetitive circuit elements and tube sockets are MAD-E. Integral T11th the ceramic building B10CK. These are assembled in skyscraper type structures, yielding a standard module for EACH. Circuit stage. Devising circuit layouts by. This approach involves planning in 3D dimensions rather than the conventional TTV0 dimensional approach heretofore employed. These standard building blocks and Mod U1ES and automation are readily adaptable to automatic machine methods. During the assembly, 10FO automatic testing is provided for components and SUBS assemblies. The resulting product SHOIIS and EX. Extremely high degree of uniformity. Flexibility is assured in that a production line can be converted in a matter of hours from building a civilian type product, such as a radio receiving set, to building complex military electronic equipment. This provides an unusual capability in standby capacity. Further proof of the flexibility is provided by the fact that a TVIDE variety of types of electronic equipment have been designed for assembly by the modular technique. The modular design and SEMB1Y also afford an unusual possibility in standard packages for sub-assemblies with attendant simplification of the maintenance and repair problems. These developments were turned over to industry about 2 years ago, and several companies are now engaged in the production of electronic items using modular techniques. Summary. This has been a long presentation 0NMY. Part, I know. But I think it was necessary to give the members of this committee a FIR1Y complete history of the development and application of techniques in automation. If I may summarize NOLV, I would make these points. Automation is not NEL-L. It is the natural outgrowth of scientific research and development in the field of mechanization. It is new only in the sense that recent advances in the field of electronics and communication can now be applied to mechanization. And just as previous advances in mechanization have helped to further our civilization and to increase zero-UR productive capacity, so automation offers promises of even greater benefit. Automation makes use of the high-speed capabilities of E1EC. Electronic data processing devices and computers. These new devices promise to serve society in several ways. They will be effective tools for increasing productivity and for production control. They will relieve considerably massive paper handling and processing problems of the nation's businesses and offices. The will be high-speed servants for the efficient management of complex organizations, such as government agencies. They offer to Sci and CE and engineering a magnificent tool for taking scientific problems which were hitherto impossible because of the length of time required for solution. These I think are the promises of the SE.NET-L machines. But I urge you to remember that this enlargement of our productive capacity comes about because of advances in mechanization, which, in turn, are dependent up an enlarged scientific program. As LIEG ROLI, TIE become more and more complex. Continued research helps us to cope with this complexity. In 38. Robot Showstoppers. Did you see our story? Magazine, March 19, pp. In LIV 173 to 176. From time to time you may need DT0 help organize a display in a business show including some device that you hope LG'll stop every person at tending the show and make him notice your display. A device which may be called a showstopper. In addition to publishing the magazine Computers and Litomation, we have for 5 years been developing and deconstructing robot showstoppers, small robot machines that respond to their environment and obey by themselves. TL_O of them are Relay-Mo, a machine that will play the game tit-tat-toe with a human being, and either win or draw all the time, or, depending and the setting of a switch, will sometimes lose, so as to make the game more interesting for the human being. Was at the IRE show, in Guardian Electric's exhibit, see FFI Picture in Life magazine. Explore a maze, find food, and squee, an electronic robot square rel that will hunt for a nut indicated by a person in the audience, pick it up in his hands, take the nut to his nest, there leave it and then hunt for more nuts. See picture in Life magazine. Besides these we have other small robots finished or under development. These machines may be rented for SHOIVS under certain conditions, so, modifications of the small bots to fit a particular Perp 0 SE are often possible. 2. Berkeley Enterprises Incorporated. 513 Avenue of the Americas R156. New York 11, NY. Please send us more information about your robot showstoppers. The advertising application L/F have in mind is underscore 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 from organization address filled in by name, title, date, transistor and digital computer techniques applied to the design, development, and application of -- Automatic radar data processing. Transmission and correlation. In large ground networks. Digital computers. Similar to successful Hughes airborne fire control. Computers are being applied by the ground systems department to the information processing and computing functions of large ground radar weapons. Control systems. The application of digital and transistor techniques to the problems of large ground radar net works has created new positions at all levels in the ground TEMS department. Engineers and physicists with experience in the fields listed, or with exceptional ability, are invited to consider joining us. Transistor circuits, digital computing, NE.TS. Magnetic drum and core memory. Logical design. Programming. Very high power modulators and transmitters, input and output devices. Scientific. Staff relations. Special displays. Microwave circuits. Culver City, Los Angeles County, California. 39. New patents. Raimono R. Skolnick. P.E.G. Patent Agent. Ford Instrument Co. DIV of Sperry Rand Corp. Long Island City 1, NY. The following is a compilation of patent TS 2,729,742 I. Frederick N. Brower, Jenkintown. PE taining to computers and associated equip PA. iFilco Corp., Philadelphia, PA. IA. Meant from the Official Gazette of the United Pulse Operated Timing Circuit. States Patent Office, dates of issue as Indy 2,729,772 I. Quarles M. Perkins I. Minneapolis. Kate. Each entry consists of patent number I. Min. I. Bendix Aviation Corp., TDERB 0R0. Inventor, S. I. Assignee I. Invention. NJ. I. A device for amplifying the USB 1A. December 27, 1955, 2,728,524/John H. Nair. Winyl.Tude, PA. I for use in an analog C0M. Computer, a timing and testing circuit for determining temperature transients by electric analogy. 2,728,882 I. Charles L. Cohen, Hyattsville MD1. ACF Industries Incorporated, NJ. IA Compute R. Stabilizing System. 2,728,886 I. Nicholas Rahutz, Scotia, NY. General Electric Co., NY. INELECT RIC. Control Circuit. 2,728,887 I. Stuart C. Rockhavelm \F, Farmington. Mich. I. Robotron Corp., Detroit, Mich. IA. Variable Voltage Rectifier System FRO MA. 3-phase line source. 2,728,899 I. Wayne M. Ross, Seattle, Washington I. Minneapolis Honey Ivel Regulator Co., Min. A. Polys, Min. IA Receiver Blanking Circuit. 4-pulse Transmission Reception Systems. 2,728,900 I. Wayne M. Ross, Seattle, Washington I. Minneapolis Leone Well Regulator Co., Min. A. Polys, Min. IA Pulse Timer and Receiver. For automatic gain control in pulsed OBJECT. Locating systems. 2,728,902 I. Harry B. White, Canton, and Mork. D. Stahl and Jack E. Duff, North Canton, Ohio I. USA. I an apparatus for supersonic ranging and detection. 2,728,907 iCarly Grunsky, Garden City N.Y.I. Sperry Rand Corp., Dell. /Servo Systems 4. Pulse Signals. January 3, 1956, 2,729,106 I James C. Matha. Sen, Pleasantville, N.Y. I Nordenket A.Y. Corp., IL. I an air-supported gyroscope. 2/29,107 I Frederick D. Braddon, B.A. by Lon. N.Y. I Sperry Rand Corp., Dell. IATHREE. Axis Gyroscopic Reference Instrument. 2,729,701 I Maurice Maes Levy, London, ENGI. The General Electric Co., Limited, London. Eng. I an electric pulse code mod U1 at ION. System for periodically generating a groupie of coded pulses representative of the instantaneous value of a magnitude which may vary within a given range. 2,729,727 I Everett W. Malloy, South San G.A. Briel, and Harold R. Schultz, Anaheim, Cal. If I Beckman Instruments Incorporated, Fullerton, California. I a variable impedance device. Signals and rejecting the spurious signal S of a signal source 2/Hitch develops SIGNA1. Voltages in response to a change in a condition to be measured. 2,729,773 I Floyd G. Steele, La Jolla, California 1. Digital Control Systems Incorporated, California. ION. Electric motor control system employing DI. Function signals. 2,729,774 I Floyd G. Steele, La Jolla, California 1. Digital Control Systems Incorporated, California. IA. Function Nonlinear Servo System. 2,729,781 I Rostvell W. Gilbert, Montclair N.J. I Weston Electrical Instrument Corp., Netvark. N.J. I an electromagnetic transformer. 2,729,807 I John O. Pavinen, Aldon, Pa. I Burr. Ruffs Corp., Detroit, Mich. I a GAT E and memory circuit utilizing magnetic cores. 2,729,808 I Isaac Levin Auerbach, Philadelphia. And John Oliver Pavinen, Aldon, Pa. IBUR. Ruffs Corp., Detroit, Mich. I Pulse Gating. Circuits and Methods. 2,729,809 I Robert G. Hester, Redondo BACH. California. IUSA. I a Polarity Selector. 2,729,811 I Paul-François Marie Glois, Paris. Father I Société d'Électronique et d'Automatisme. Paris, Father I a method of electrically converting a number in a numeration system into a number of another numeration system of an order inferior to the first numeration system. 2,729,812 I Dale M. John, Garden City, NY. Sperry Rand Corp., Dell. I an apparatus for converting digital information to an analog voltage. January 10, 1956, 2,730,300 I Henry C. Savino. Hackensack, NJ.IIA Computing and Indicat. Ing system for showing deviations from a control unit. 2,730,301 I Bernard Delacour Beamish, Neuro. Shell, NY. IE an electric can co-unter. Circuit for counting objects moving along a common path. 2,730,568 I Leon H. Reagan, Richland, Washington I. General Dynamics Corp., Dell. IASTAR G. Next idle register. 2,730,573 I Hugh Brougham Sedgefield, Barn S. Common, London, and Frederick Arthur Summer. Lynn, Lee, London, Eng. I The Sperry Gyroscope. Coty Limited, Brentford, Eng. A Phi DBACK. Amplifier system and servo mechanism that is adapted to respond to input changes at very. Content on page 42. 40. Did you see our story in Life Magazine, March 19, pp 173 to 176? Make your own baby genius computers with GENIAC. Electric Brain. Construction Kit Number 1. Diagram of the Versa. Tile multiple STDTCH. Which can be assembled to make any STVITCH. Combination from 16 decks of 2 positions to 2 decks of 16 positions. This kit is an introduction to the design of arithmetical, Logica 1, reasoning, comrouting, puzzle Sol 61 LJ. And game-playing circuit TS. It is simple enough for intelligent boys to assemble, and yet is instructive to computer men because it shows how many kinds of computing and reasoning circuits can be made from simple components. With this kit and 64-page manual, you can easily make over 30 SMA11 electric brain machines that exhibit intelligent behavior. Each runs on one flashlight battery. All connections high th nuts and bolts, no S01. Deering required. Price $17.95, add ADT for shipment in USTVEST of Mississippi, $1.80 for shipment outside US. If not satisfactory, returnable in 7 days for full refund. A few of the machines you can make: logic machines, reasoning, syllogism machine, intelligence testing, game playing machines, NIM, TIT TATTO, arithmetic machines, adding, SUB, tracting, multiplying, dividing, carrying, etc. Cryptographic machines, secret coder and decoder, combination locks, puzzle machines, the space ship airlock, the Fox Hencorn and hired man, Douglas MacDonald's will, the uranium ship and the space per 8s. Mail this request or a copy of it. Berkeley Enterprises Incorporated, 513 Avenue of the Americas R156, New York 11, NY. Please send me GENIAC Kit AO1 and manual. Price $17.95, add TLO cent for shipment in U.S. west of Mississippi. $1.80 for shipment outside U.S. 1 enclose in full payment. If in good condition, it is returnable in 7 days for full refund. My name and address are attached. Opportunity in Southern California. Asterisk. Excellent salaries for JIJ, 2CGI tall. Who can fill key creative posts. In long range, non-military. Research and design. For advanced business. Computer systems. Asterisk. Engineer electronics. Engineers. To specialize in research and design. For advanced business computer SYS. TEMS. Must have exceptional creative ability, plus knowledge of vacuum tube circuit design, transistor circuitry. Asterisk. Senior digital computer transistor circuitry. Engineers. For projects in advanced computer design, development APD application. Must have thorough knowledge of digital computer logic and circuitry. Input-output devices, programming. Engineers. For advanced research and design in computer transistor circuitry. Capabilities should include ability to direct others in new project work. Opportunity for electronic or electrical engineers. Background in one or more of the fields below equips you for excellent career positions with NCR Electronics Division. Logical design. Ferroelectrics magnetic cores. Computer systems. Transistor circuits. Input-output devices. Applications of physics. Computer systems specs. Def. Of system requirements. Ground floor opportunity with unusual stability. Openings listed here are for the basic organization of the NCR Electronics Division. If you qualify for one of them, you'll be a key member of this fast-developing division of one of America's top companies. You'll enjoy the freedom of a small, select research group, operated by engineers for engineers, as well as the exceptional financial stability of a large, long-established firm. A full program of employee benefits, too. New, modern, air-conditioned plant with every modern research and development facility in a conveniently situated Los Angeles suburb. Star. For illustrated company brochure, write Director of Personnel. Asterisk. RRADEMARIC. National Cash Register Company. ELECT RON ICSDIVISI on 3348 West El Segundo Beefid, Hawthorne, California. 41. Cont D from page .40. 10 WFJ, Equincies. Computers and Automation. 2,730,574, Frederick H. Belzy, Sale, Eng. General Electric Co., NY. A multi-stage magnetic amplifier having a plurality of push-pull connected stages in cascaded connection. 2,730,576, Robert S. Carruthers, Mountain Lakes, NJ. Bell Telephone Lab, Inc. Network, NY. A miniaturized transistor amplifier circuit. 2,730,617, George H. Marmont, Hollywood, Cal. If, and Bernard M01 Ivor, Morris TMVN, NJ. /Bell Telephone Lab, Inc., New York. NY. /A timing circuit. 2,730,619 Willip S. Parnell, Glen Burnie. And John W. Taylor, Jr., Baltimore, MD. USA. An oscillator control. 2,730,620, Otto H. Schmidt, Minneapolis, Minnesota, and Winfield E. Fromm, Roslyn, NY. Airborne Instruments Lab, Inc., Mineola, NY. /A variable frequency signal genera. Tor. 2,730,624 Alvin Honnold, Little Silver, N.J/ USA, a frequency multiplier circuit. 2,730,632 Daniel L. Curtis, Venice, California / Hughes Aircraft Co., Dell. / A diode gating. Circuit T. 2,730,657, Stuart C. Rockefeller, Farmington, Mich. / Robotron Corp., Detroit, Mich. / A. Multiple phase control system. 2,730,658 Willem 6, Eindhoven, Neth. / Hartford National Bank and Trust Co., Hart. Ford, Con. / An apparatus for counting PW. SES. 2,730,676 Ronald Hugh Barker, Christchurch, Eng. / National Research Development Corp. London, Eng. / A cyclic permitting pulse code. System. January 17, 1956, 2,731,199 Ioino Gertman. And Edmund Febvard, Saint Monde, Father / Inter. National Business Machines Corp. /net / York. NY. / A computing mechanism for checking computations. 2,731,200 Albert C. Kolsch, Jr., Poughkeep. SIE, NY. / International Business Machines Corp., New York, NY. / A combined record sensing and storage system. 2,731,201, Leonard R. Harper, Poughkeepsie, NY. / International Business Machines Corp., New York, NY. / An electronic counter-com. Prizing at least 4 BIST-able devices con. Necked in cascade. 2,731,203 James G. Miles, Minneapolis, Mem / Sperry Rand Corp., Dell. / A saturable core circuit for counting and the like. 2,731,519 Robert W. Bordouillac, Southborough, Mass. / More Electronic Lab, Inc., War. Cester, Mass. / A special low impedance out. Put circuit for high chain bridge amplifier. 2,731,521 Jack A. Crawford, China Lake, Cal. If. / USA. / A magnetic amplifier. 2,731,571 Button Chaws, Cambridge, Mass. USA. / A delay circuit. 2,731,594, Stuart C. Rockefeller, Farmington, Mich. Roboter.on Corp., Detro. T. Mich. N. Apparatus for simultaneously shifting the phase of each phase circuit of a multi-phase system. 2,731,595, George R. Gamertsfelder, Water. Town, Mass. USA. A phase-shifting CIR. Quit comprising an impedance network made up of resistance and inductive elements. January 24, 1956, 2,732,497 Robert D. Hahn. Koch, Compton, California. / Northrop Aircraft, Inc., Hadthorne, California. / A pulse generator. 2,732,504 Floyd G. Steele, Long Beach, Cal. If / Northrop Aircraft Incorporated, Hawthorne, California. / a linear cam computer. 2,732,505 / Alec Hervey Bennett Walker and Kenneth G. King, London, Eng. Westinghouse. Brake and Signal Co., Limited, London, Eng. / an electric control apparatus. 2,732,520 / Georges René Covenalt, Vitry-sur Seine, Father / Société Alsacienne de Construc. Chins Mécaniques, Paris, Father, an electrical servo mechanism. And _ comma dash. Bulk subscription rates. These rates apply to subscriptions coming in together direct to the publisher. For example, if 5 subscriptions come in together, the saving on each 1-year subscription TV will be 24%, and on each 2-year subscription LVI 11 be 31%. The bulk subscription rate is depending on the number O.F simultaneous SUB script ions received, follow. Bulk subscription rates. United States. Number of simultaneous subscriptions. 10 or more. 5 to 9. 4. 3. 2. Rate for each subscription, and resulting saving to subscriber. 1 year 2 years. $3.80, 31%, $6.60, 37%. 4.20, 24, 7.25, 31. 4.60, 16, 8.00, 24. 5.00, 9, 8.80, 16. 5.25, 5, 9.55, 9. For Canada, add 50 cents for each year, 0 UT. Side of the United States and Canada, add $1 for each year. : 1 star. Special issues of Computers and Automation. The June issue of Computers and Automation, commencing with June 1955, is a special issue, the computer directory. For detail is about the next comput directory, see the computer directory, 1956. Asterisk ties. 42. Dash 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 1. A key technical position with a fast-growing II. New unit of GE is now open. It involves guiding and integrating extensive analysis of bomber defense systems, including missiles, to determine modern bomber armament requirements. To handle this complex operation, you should have 7 to 9 years experience in the field of aircraft defensive armament or missiles SYS. TEMS, a BS in physics, engineering physics, math, or engineering, and experience and familiarity with digital analog computers. The Aircraft Products Department, formed only 3 years ago, is expanding rapidly and has much to offer the career-minded engineer. Its location is exceptionally fine for living and working. Write in confidence to Mr. C. E. Irwin. Engineering Administration. AIRCRAFF Products Department. General_Electric. 600 Main Street, Johnson City, NY. L underscore 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 Aegea. Pioneers in inertial Navigation. Immediate openings for supervisory and staff positions as well as for senior engineers, and associate engineers experienced in stabilizing devices systems evaluation, servo mechanisms gyroscopics, automatic controls digital computers, thermodynamics accelerometers, optics telemetry, environmental research guidance systems, transformers. ARMA, recognized for its accomplishments in the fields of navigation and fire control, is a leader in the development of inertial navigation. This new system deals solely with space, time, and acceleration, acting independently of external influences. Creative engineering of the highest order is required to develop components making inertial navigation possible. Accelerometers to measure acceleration. Integrators to convert this information into velocity and distance, gyros to provide directional reference and hold the system stable, computers to calculate course to steer and distance to go. Components must meet rigid weight and size requirements and function with undreamed of accuracy. ARMA, one of America's largest producers of ultra-precise equipment, offers unlimited opportunity for engineers to help in this great endeavor. Challenging projects and ARMA's extensive supplementary benefits make an ARMA career doubly attractive. Send resume to 111.11 Technical Personnel Department 2500 IW Division of American Bosch ARMA Corporation, Roosevelt Field, Guard City, Long Island, NY. 43. Computers and Automation, back copies. REFERENCR, information, with notes regarding latest issues containing same organizations. Roster of organizations in the COMPUTER field, December 1955. Roster of Computing Services, December 1955. Roster of Consulting Services, June 1955. Computing Machinery and Automation. Types of Automatal Computing Machinery, December 1955. List of automatic computers, February and April 1955. Outstanding examples of automation, JU1Y 1954. Commercial automatic computers, December 1954. Types OI components of automatic computing machinery, March 1955. Products and services in the computer field. Products and services for sale, June 1955. Classes of products and services, June 1955. Words and terms. Glossary of terms and expressions in the computer field, January 1956. Information and publications. Books and other publications, many issues. Net patents, nearly every issue. Roster of magazines, December 1955. Titles and abstracts of papers given at meetings, many issues. People. Myos who in the computer field, June and September 1955. June, the computer directory, 1955, 164 pages. Part 1, Who's Who in the Computer Field. Part 2, Roster of Organizations in the Computer Field. Part 3, The Computer Field, Products and Services for Sale. July, Mathematics, the Schools, and the Oracle. Alston S. Householder. The application of automatic computing equipment to savings bank operations are Hunt Brown. The book reviewer Rose Orant. Linear Programming and Computers, PARTI. Chandler Davis. August, the automation of bank check processing. R. Hunt Brown. Linear Programming and Computers, Part 2. Chandler Davis. Justifying the use of an automatic computer. Ned Chapin. Charting on automatic data processing systems. Harry Eisen Press, James L. McPherson, and Julius Shiskin. A rotating reading head for magnetic tape and Wire National Bureau of Standards. Some Curiosities of Binary Arithmetic Yosfa 1. In Testing Binary Computers Andre 1 FD. Booth. September, A Big Inventory Problem and the IBM 702 Neil MacDonald. 44. Publications for Business on Automatic C0LLL Uters. A Basic Listing Ned Chapin. Franchise Isaac Asimov. Automatic Coding for Digital Computers GM. Hopper. Automatic Programming, the A2 Compiler System. Part 1. October, The Brain and Learned Behavior Dr. Harry F. Harlow. Automatic Programming, the A2 Compiler System. Part 2. Who are manning the new computers? Joe N. M. Breen. November, Automatic Answering of Inquiries L. E. Griffith. Found, A Lost Moon Dr. Paul Herget. Mr. Andrew Lloyd R. W. Wallace. December, Digital Computers in Eastern Europe. Alston S. Householder. Automatic Airways Henry T. Simmons. January 1956, Machines and Religion Elliott. Grunberg. Automatic Coding Techniques for Business DATA. Processing, Directions of Development. Charles W. Adams, Bruce Moncrieff. What is a computer? Neil D. MacDonald. February, The Function of Automatic Programming. For Computers in Business Data Processing. R. E. Rosheim. Computers and Engineering Education Paul E. Stanley. The Planning Behind the IBM 702 Insta 11 at ION. At Chrysler Corporation Eugene Lindstrom. March, Organization of a Programming Library for a Digital Computer Center Werner L. Frank. Growth of IBM Electronic Data Processing OPER. Asians on the West Coast Neil D. MacDonald. Translating Spoken English into Written Word S. E. C. Berkeley. IBM Trust Suit ended by decree. Back copies, price, if available, $1.25 EACH. Except June, 1955, $4. Volume 1, No.Lsept. 1951, to Volume 1, Number 3, July, 1952, Out 0F. Print. Volume 1, Number 4, October 1952, in print. Volume 2, Number 1, January 1953, to Volume 2, Number 9. December 1953, in print, except March, Number 2. May, Number 4, and July, Number 5. Volume 3, Number 1. January 1954, to Volume 3, Number 10, December 1954, in print. Volume 4, 1955, Number 1 to 12, in print. A subscription, see rates on page 4, may be specified to begin with the current month's or the preceding month's issue. Write to Berkeley Enterprises Incorporated. Publisher of Computers and Automation. 513 Avenue of the Americas. New York 11, NY. Mathematical analyst Keith Cursory loads jet transport flutter problem into one of Lockheed's 2701 so on order, 2. 704s to help keep Lockheed in front of numerical analysis and production core data processing. 704s and 701 speed. Lockheed research in numerical analysis. Lockheed Burbank. With two 701 digital computers already in operation, Lockheed has ordered two 704s to permit greater application of numerical analysis to complex aeronautical problems now being approached. Scheduled for delivery early next year, the 704s will replace the 701, so much of the work scheduled or in progress is classified. However, two significant features are significant to career-minded mathematical analysts. 1. The wide variety of assignments created by Lockheed's diversified development program, and 2. The advanced nature of the work, which falls largely into unexplored areas of numerical analysis. Career positions for mathematical analysts. Lockheed's expanding development program in nuclear energy, turboprop and jet transports, radar search planes, extremely high speed aircraft and other classified projects has created a number of openings for mathematical analysts to work on the 704s. Lockheed offers you attractive salaries, generous travel, and moving allowances which enable you and your family to move to Southern California at virtually no expense, and an extremely wide range of employee benefits which add approximately 14% to each engineer's salary in the form of insurance, retirement pension, etc. Those interested in advanced work in this field are invited to write E.W. Deloria's, Department Ma 31-4. Aircraft Corporation California Division. California. 45. Advertising in Computers and Automation. Memorandum from Berkeley Enterprises Incorporated. Publisher of Computers and Aljtot Asian. 513 Avenue of the Americas. New York 11, NY. 1. What is Computers and AUFOMATION? It is a monthly magazine containing articles, papers, and reference information related to computing, machinery, robots, automatic control, cybernet, ICS, automation, etc. One important piece of reference information published is the roster of organizations in the field of computers and automation. The BAS-IC subscription rate is $5.50 a year in the United States. Sin G1E. Copies are $1.25, except June, 1955, the Computer Directory, 164 pages, $4. For the titles of articles and papers in recent issues of the magazine, see the back copies page in this issue. 2. What is the circulation? The circulation includes 2,000 subscribers, as of Feb 9/0, over 300 purchasers of individual back copies, and an estimated 2,500 non-subscribing readers. The logical readers of Computers and Automation are people concerned with the field of computers and automation. These include a great number of people who will make recommendations to the IR organizations about purchasing computing machinery, similar machinery and components, and whose decisions may involve very substantial figures. The print order for the APR issue WA5 2,700 copies. The overrun is largely held for eventual sale as back copies, and in the case of several issues the overrun has been exhausted through such sale. 3. What type of advertising does compute ours and automation take? The purpose of the mag AINE is to be factual and to the point. 4. This purpose the kind of advertising wanted is the kind that answers questions factually. We recommend for the audience that we reach, that advertising be factual, useful, interesting, understandable, and new from issue to issue. We reserve the right not to accept advertising that does not meet our standards. 4. What are the specifications and costs? 0f. Advertising. Computers and AUFOMATIONIS pub. Listed on pages 8x11, ad SIE, 7x10. And produced by photo offset, except that print ed sheet advertising may be inserted and bound in with the mega INE in most cases. The class ing date for any issue is approximate 1 YTHE 10th of the month preceding. If possible, the company advertising should produce final copy. For photo offset, the copy should be exact IY as desired, actual size, and assembled, and may include typing, writing, 1 in EDRO WinG, printing, screened halftones, and any other. 46. Copy that may be put under the PH0FF set. Camera without further preparation. Unscreened. Photographic prints and any other copy requirement. Additional preparation for photo offset shall 1d be furnished separately, it will be prepared, finished, and charged to the advertiser at small additional costs. In the case of printed inserts, a sufficient quantity for the issue should be shipped to our printer, address on request. Display advertising is sold in units of a full page, ad sh, etx10, basic rate, $190, 2/3 page, basic rate, $145, comma, and half pagi. Basic rate, $97, back cover, $370, in city. Front or back cover, $230. Extra for color red. Full pages only and only in certain positions. 35%. 2-page printed insert, 1 sheet, $320. 4-page printed insert, 2 sheets, $590. Classified advertising is sold by the 11/0 RD. 60 cents a word, WITH a minimum of 20 words. 5. Who are our advertisers? Our advertisers in recent issues have included the following companies, among others: Aircraft Marine Products Incorporated, American Bosch Corp., Ampex Corp., Armor Research Foundation, Arnold Engineering Co., Automatic Electric Co., Bendix Aviation Corp., Cambridge Thermionic Corp., EBSCO Incorporated, Ferranti Electric Co., Ferroxco Corp of America, General Electric Co., Hughes Research and Development Lab, International Business Machines Corp., Lockheed Aircraft Corp., Lockheed Missile Systems, Logistics Research Incorporated, The Glenn L. Martin Co., Monrobot Corp., Norden Kete Corp., Northrop Aircraft Incorporated, GOGEA Philbrick Researches Incorporated, Potter Instrument Co., Ramo Wooldridge Corp., Reeves Instrument Co., Remington Rand Incorporated, Republic Aviation Corp., Sprague Electric Co., Sylvania Electric Products Incorporated. Publications: P34, LINEAE Programming and Computers. Reprint of 2. Articles by Chandler Davis, in July and August 1955. Computers and Automation. A clear, well-written introduction to linear programming waifu. Emphasis on the ideas. $1.20. P2D, the COMPLJFER Directory, 1955. 164 pages, 7,500 Who's Who entries. 300 organization entries, and 600 entries of products and services for sale in the computer field, 250,000 words of condensed factual information about the computer field, June 1955 issue of Computers and Automation. $4.00. P32, Symbolic Logic, by Lewis Carr. Roll. Reprint of Symbolic Logi C. Part I, Elementary, 4th edity CLL, 1897. 240 pages, by Lewis Carroll, C.L. Dodgson. Contains Lewis Carroll's inimitable and entertaining problems in symbolic logic, his method of solution, now partly out of date, and his sketches of parts 2 and 3, which he never wrote since he died in 1898. $2.50. P25, Numbles Number Puzzles for Nimble Minds. Report. Conti A in S. Collection of puzzles like Try. I. HAVEINTRAIN. For the SE Fun Your. Wit S. Equals tvas ways in tons. Y equals VIF. In fact, you can also, 90,893 85,202. 44,393 29,081, solve for the digits. Each letter stands for just one digit. 0 to 9. All are new numbles, additions, multiplications, etc. J. Some easy, some hard. Each WITH 2 messages, 0 any. Open, 1 hidden. Hints for solution. Good exercises in logical reasoning. $1.00. Mail this coupon. Or copy it. Edmund C. Berkeley and Associates. 815 Washington Street R15B. Newtonville 60, Mass. Please send me publications circled. And your announcement of publications. 2D253234. I enclosed $ in full payment. Add 10 cents per item to cover cost T0F. Handling and mailing. It is understood that if I am not satisfied, I may return any item within 5 days after receiving it, and you will at once refund my money. My name and address are attached. Ferranti. High-speed tape reader. The Ferranti high-speed tape reader accelerates to full speed within 5 milliseconds and stops within 3 milliseconds. It has been in use at leading computer installations for over 2 years and has achieved a sound reputation for simplicity and reliability in regular operate on. TG1 Mark II model reads at speeds up to 200 characters per second, and stops the tape from full speed within a character position. Within 0.03 inch. The tape is accelerated to full speed again in 5 milliseconds. And the following character is ready for reading within 6 milliseconds of rest position. 2. Mark II model reads at speeds up to 400 characters per second. And stops within 0.1 inch. ILF2I both models read either 5-level, 6-level, or 7-level tape. By simple adjustment of an external lever. .imfr The tape is easily inserted without complicated threading. Lap or butt splices are taken without any difficulty. The same tape may be passed thousands of times without appreciable tape wear. The optical SYSTT M has no lenses or mirrors to get out of alignment. Friction drive is independent of sprocket hole spacing. Large output amplifiers are included for each channel, including a special squaring circuit for the sprocket hole signal. Output swing between hole and blank is greater than 20 volts. 47. Dimensions, 91C x 11V2 x 11V.S weight, 37 IBS. For use with long lengths of tape up to 1000 feet, spooling. Equipment operating up to 40 inches per second for take-up or supply is available separately. Ferranti Electric Incorporated. 30, Rockefeller Plaza, New York 20, NY. Advertising Index. The purpose of computers and automation is to be factual, useful, and understandable. For THPU. Pose, the kind of advertising we desire to publish is the kind that answers questions, such as, what are your products? What are your services, and d. For each product, what is it called? What does it do? How does it work? What are its LIN specifications? Fol 01 DNG is the index and a summary of advertisements. Each item contains name and address 0f. The advertiser / subject of the advertisement / page number where it appears / CA number in case of inquiry, see note below. Ampex Corporation, 934 Charter Street, Red 1/100D. City, California. / digital magnetic tape trans. Port / page 49 / CA number 110. Arma Division American Bosch Arma Corp., Ruse. Veltfield. Garden City, LI, NY. /ENGI. Opportunities / page 43 / CA no. 3. Arnold Engineering Co., Marengo, Ill. / Bob Bin. Course / page 5 / CA number 112. Berkeley Enterprises. Inc. 513 Ave of the Amer. ICAS New York 11, NY. / Robot Showstoppers. Geniac Kid Publications / pages 3941,47 / CA number 113. Cambridge Thermionic Corp., 447 Concord AVE. Cambridge 38, Mass. / Computer Components / page 2 / CA number 114. Computers and Automation, 513 Avenue of the Amer. ICAS New York 11, NY. / Back copies, Edver. Tising / pages 44, 46 / CA number 115. Cudahy Publishing Co., 6141 North Cicero Avenue Chi. Cago, Ill. / Automatic Data Processing SER. Vice / pages 25, 26 / CA number 116. Electrodata Corporation, Pasadena, California. / AP. Applications Specialists / page 36 / CA number 117. Ferranti Electric Incorporated, 30 Rockefeller Plaza. New York 20, NY. / High-Speed Tape READR / page 47 / CA number 118. Ferox Corp., Eastbridge St., Saugerd IES. NY. / Magnetic Core Materials / page 31 / CA number 119. General Electric Co., Aircraft Products 0 EPT. 600 Main Street, Johnson City, NY. /he1p. Wanted /page 43 /CA number 120. General Electric Co., Hanford Atomic Products. Richland, Washington /help 2 /anted /ph. 37 /CA number 121. Hughes Research and Development Laboratories. Culver City, California. /employment opportunities / page 39 /CA number 122. Lockheed Aircraft Corp., California DIV. Burbank, California. /mathematical analysts wanted /page 45 /CA number 123. National Cash Register Co., Electronics DIV, 3348. W. E1, Segundo Boulevard, Hathorne, California. /did. GI Tal Computer Engineers /page 41 /CA number 124. RCA, Service Co., Inc., Missile Test Project. P.O., Box 1226, Melbourne, FLA. /help wanted / page 31 /CA number 125. Sylvania Electric Products Incorporated, 175 Grade AR. Row Ave, Buffalo 7, NY. /matched Transis. Tours /page 50 /CA number 126. Reader's Inquiry. If you wish more information about any products or services mentioned in one or more of these advertisements, you may circle the appropriate CANOS on the Reader's Inquiry form below and send that form to us. We pay postage. See the instructions. We shall then forward your queries, and you will hear from the advertisers direct. If you do not wish to tear the magazine, just drop us a line on a postcard. ******. Reader's Inquiry FDRM. Enclose form in envelope T. Paste label on envelope. Dash. ITI. II. Z2. 0. IA Reader S Inquiry Form I. C. 0. C. IN. 0 G. M. N. Dash plus. I. 0 1. LC. Z. AICD. M. Colon 0. M. M. ZCD. I. M. Colon 0. C. C. Z. U. Colon 0. 6. M. 0. Dash OJ. Z. FL. Z. M. N. N. M. R. Tongue sticking out, OJ. M. R. E. TJ. I. Name, please print. Your address. Your organization. Its address. Your title. Underscore. Please send me additional information on the following sub-ICs for which I have circled the CA number. 1 2 3 4 5 26 27 28 29 30 51 52 53 54 55 76 77 78 79 80 101 102 103 104 105 126 127 128 129 130 6 7 8 9 10 31 32 33 34 35 56 57 58 59 60, 81, 82, 83, 84, 85, 106, 107, 108, 109, 110, 131, 132, 133, 134, 135. 11, 12, 13, 14, 15, 36, 37, 38, 39, 40, 61, 62, 63, 64, 65, 86, 87, 88, 89, 90, 111, 112, 113, 114, 115, 136, 137,138, 139, 140. 16, 17, 18, 19, 20, 41, 42, 43, 44, 45, 66, 67, 6,869, 70, 91, 92, 93, 94, 95, 116, 117, 118, 119, 120, 140, 142, 143, 144, 145. 21, 22, 23, 24, 25, 46, 47, 48, 49, 50, 71, 72, 73, 74, 75, 96, 97, 98, 99, 100, 121, 122, 123, 124, 125, 146, 147, 148, 149, 150. Remarks. 1111111111111 underscore 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 J underscore 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 48. New. Digital. Magnetic. Tape. Transport. The MPEX FR200 for digital handling provides new performance standards, new convenience features and an unmatched excellence of design. New ease of tape change. The time-saving feature of single-loop threading is provided by a lever which moves the idlers into a straight line. This arrangement eliminates chance of faulty threading by unskilled personnel. New machine-to-machine tape compatibility. All MPEX FR200 tape transports are manufactured to exact standards that permit tapes recorded on one to be reproduced on any other. MPEX to MPEX compatibility is guaranteed, and at no extra cost. New plug-in heads to match other tape transports. The MPEX FR200 uses self-aligning plug-in head as assemblies. These can be furnished to match other digital or analog tape recorders to permit tape interchange. A second head stack for monitoring or off-tape parity checking can also be added if desired. High-speed start and stop. On the MPEX FR200 the tape attains full speed or full stop within less than 5 milliseconds to provide high information storage density. A remote control provision is provided, as well as push buttons on the top plate. New standard of excellence. The FR200 brings to digital applications the reliability, durability and adherence to specification that have made MPEX tape recorders the most widely used in instrumentation. New low prices beginning at $2,675. The base price of $2,675 is for a complete FR207 TB tape transport, with 7-track head, 4% inch tape up. Aerating at 30 IPS tape speed. Prices will be quoted on machines with other tape speeds, multiple speeds, other tape widths and other heads. Full specifications on the FR200 and description of --934 Charter Street. Its features and accessories are given in descriptive literature. Redwood City. FQR your copy, right department. VV 2539 California. District offices, New York, Chicago, Atlanta, Dayton, Redwood City, Silver Spring, Maryland, Washington D.C. area. Distributors, Radio Shack, Boston, Bing Crosby Enterprises, Los Angeles, Southwestern Engineering and Equipment, Dallas. And Houston, Ampex American in Canada. 4V. BYLvania NL, and Transy STORs. Whatever the front-end design in your transistor. Audio circuits, Sylvania offers a highly efficient audio transistor lineup for driver and PUSH pull stages. Controlled driver characteristics and a matched push-pull pair assure maximum power output with minimum distortion. Driver stage. Sylvania's 2N35 for Class A driver use has linear characteristics at high current levels, thereby ensuring maximum input to the push-pull stage. With minimum distortion. Push-pull matched pair. Output transistors in Sylvania's audio lineup are matched to within 10% on collector current. Characteristics. The close tolerances to which the 2N35 push-pull pair is produced permit maximum power gain with minimum distortion as plotted in Figure 1. Power output of the 2N35 pair is rated for a minimum of 100 MW at 50 degrees Celsius. Dissipation is rated at 50 MW per unit, with higher rated counter parts available. The all-important facilities, Sylvania is equipped to supply you with production quantities, so why not call your Sylvania representative for samples or write for complete data. Address Department D20R Sylvanique Sylvania Electric Products Inc. 1740 Broadway, New York 19, NY. In Canada, Sylvania Electric, Canada, Limited. University Tower Building, Montreal. Lighting, radio, television, electronics, atomic energy. R.